We are live, guys. Hello, everyone.
Hello, everyone. Hey.
And welcome to the Zenoh User Meeting 2025. Well, we have a subset of the Zenoh team here to welcome all of you. And I think I will do the rest of the introduction and we'll take it from there. So we are here, let's say, in a Zeta scale living room, right? So this will be feeling like a living room, but that's the way in which we like it. And so we are good to go. I would say let's go because we have an agenda packed with presentations. So I'm gonna share my screen and officially get the Zenoh User Meeting 2025 started. So my screen should be coming up anytime soon. Here we go. And again, big thanks to Francesco because it's Francesco that does our comics. And he made another cool one. He had, I think, another very good idea for this one. So, Francesco, not sure if you're online, but big thanks because the community loves your comic. We love your comic, and I think you helped us giving Zenoh, a face and a body. I mean, guys, install yourself, relax. I mean, we are in our living room, right? Okay, so what is the agenda for today? Opening remarks. It's now. And in fact, it's kind of done. We are going to jump immediately into 1 year of Zenoh. As per our tradition, we will look at what we achieved in this 1 year and where we are going. And then we'll start with the Zenoh user reports, where we will be essentially having Aaron from Intrinsic explaining how they're using Zenoh in the Open RMF. We will have David from Ubiquity Robotics telling us what they are doing at Ubiquity with Zenoh in order to revolutionize the way in which embedded things talk with each other and making robots much simpler to build. Edgar for Bonsai Robotics, again, sharing another user experience on Zenoh in robotics. Then Guillaume, that many of you probably know from Dexory, telling us stories about using Zenoh and actually deploying Zenoh on live, on it out to their customers. Then we'll have Alejandro from OSRF Foundation, which will make a little bit the point of Zenoh in ROS. And we'll conclude with Leonard. And I think this is a good example, Leonard, because, some of these folks we already know and we work closely. Leonard was part of our Discord, reached out because they did a very cool security project on Zenoh, wanted to share. So thank you, Leonard, for reaching out. And here is your slot. Then we'll conclude and just go back to work for another 1 year until the 2026 Zoom. So what did we do this year? So this year we had 3 releases. The first one was Hong on July. And obviously from 1.0 release, we had several minor releases that were improving things here and there. Zenoh 1.0 was pretty big effort. And I think these are the 3 most iconic releases that we have had throughout the year. Why is Ong important? Ong is very important from my perspective because that's the first release in which we broke the 10 million message per second record. If you look at 1.0 on hardware like my Apple M2, we were at a little bit above 5 million message per second, of course, for small data. And with this release, it's the first time we went above 10 million. And again, I'm pretty sure that we can go over that. Then there were quite a few review of the shared memory API, which still remains unstable to date because there are lots of innovation we are doing in shared memory. And it was the first wave of simplification, right? So for those of you that have used the shared memory API, all of a sudden you weren't forced anymore to understand what a layout was. So for 80% of the use case, the API was greatly simplified. Besides that, we did some wire and runtime optimization that reduced the wire overhead, and as a consequence, improved, I would say, overall the throughput of shared memory, even when you're not sharing very big data. Okay, because usually, what we say is that it makes sense to use shared memory if you're sending something that is at least 1 kilobyte. With those wire optimization, we moved the threshold around 512 to 256 byte. Then we added the SCP support. What is that? Well, that is also known as type of service support, and this allows you to give hint to your switches, to your router on how to treat Zenoh traffic. So if you're streaming real-time data over Zenoh, you probably want to assign it to real-time DSCP traffic class so that your router can deal with it in the right way. We added support for Quick Datagram. So Quick was already in place, but this is something we just added in July 2025, and we finalized the TypeScript API. In October, we had another release where we had yet more innovation on shared memory. So share memory, right, up to ONG would allow you to just allocate a buffer and put whatever you want inside and stream it around. In 160 or 16x, we add the typed allocator. So all of a sudden, you can provide in Rust a structure with C representation, right, and allocate memory out of shared memory for that structure. And we showed, along with Dimitri, a bunch of examples. So there is still a repository on Zetascale that show how you can use this, for instance, to implement shared memory channels at the Zenoh level. So there are some pretty cool examples that we showed in the webinar that was just around that time. We added support for shared memory in Python. So I think that's a very good extension and addition, especially for those of you that are into robotics and AI. Some major scalability improvement and some important bug that was fixed back then. Then we added new shell for Zenoh. So that's something pretty neat that did Mahmoud. I still think that is underknown because the new shell is pretty cool and the news is even cooler. So, I mean, if you haven't tried it, check it out, build it, and just have fun with it. Added record and replay, TLS support for Zenoh Pico, and advanced pub/sub for Zenoh Pico 2. And here we land in Jiaolong, which is the last release of the year that we just released yesterday. So to make the wait a little bit sweeter for you, because we are pretty sure that you couldn't wait for Zoom 2025. So here we dropped a new release. And what this includes is querying acceleration, which is a feature that has been asked for quite some time by the user. We have now added co-localization optimization in Zenoh Pico. Check out the blog, because now if you have local pub/sub or local query, obviously the latency is in the order of hundreds of nanoseconds because it's zero copy and everything remains local. We exposed in this release the shared memory allocator used by the transport. So you can leverage those, monitor those, which is quite important, so you can see the level of utilization and so on and so forth, and support for Wireshark 4.0. Okay. So what else? Well, this year, big news was obviously Zenoh RMW becoming tier 1, right, guys? So that was huge effort from our team, the intrinsic team, and overall the community that helped at testing it. Many robotics company that will be presenting today. So once again, thanks a lot, guys. We would have not made it without all of your support, because testing was essential. And I think that thanks to that testing, we rolled out an RMW that is pretty solid, and as we will see, is already getting into production, right? But there is more. As I mentioned before, we released R2, which is a record and replay service for recording just about anything. What does that mean? Well, those of you know Zenoh, and you know that Zenoh is a protocol, but is a protocol that makes it very easy to integrate with other protocols, because we have protocol plugins in our runtime. And we have several protocol plugins for MQTT, for DDS, and so on and so forth. As a consequence, our R2, although it uses Zenoh at the core, allows you to record data from Zenoh, from MQTT, from DDS, and then perhaps replay it on any combination of those technologies. We did a webinar with Mahmoud a couple of months ago. So if you want to learn more, check it out. And again, if you want to try it out, just reach out. And then we started another experiment. Little bit of a crazy experiment, but I think it's leading into something. So the question that we were asking ourselves, and then in fact the community was asking us, was, can we have something that provides ROS features but is entirely built in Rust? And so we said, if we were to do that, obviously there are some very good initiatives in the ROS2 ecosystem, but in that ecosystem, as of today, you still have to bring in dependency from C. And what we wanted to have is something that was Rust native, right? Uh, Pure Rust and Rust fill at 360 degree. In other terms, I just need to do, add the cargo dependency, and that's it. Cargo build, and it should just work. And ideally interoperate with ROS2. So this is what we did. And while doing that, we said, well, if we do this, it would be also interesting to see what we get if we try to minimize the number of layers, because we will use Zenoh as a transport, right? So we don't need RMW. RCL will be making lots of assumption because of the fact of having Rust. So how small can we make such a stack that provides you ROS abstraction, it's interoperable with ROS, and it's fully built with Zenoh? Well, the answer was ROS-Z, and the actual answer is that ROS-Z is a very thin layer, which is less than 2,000 lines of code as of today. So, and again, this was made possible to the commitment and the incredible effort from Yuyuan. So, thumbs up, Yuyuan. And obviously, the rest of the team working on and helping driving the direction of ROS-Z. So this provides, again, Rust2 native abstraction for Rust native abstraction for ROS2. It supports already multiple message serialization formats. So you can still use ROS messages, which as a description language, and then have those messages serialized using CDR as it is done in ROS. You can use Rust structs to define your messages and then still serialize in CDR, which means interoperate with ROS. And this is probably what a Rust programmer would do. We already provide you built-in support for all ROS standard messages. But if you have applications that are using protobuf or anything CERDE, that would also work for us. And if we take, a bird's eye view, this is how, it looks like. So one thin layer on top of which you can build a Rust native ROS application or ROS-like application that are wire interoperable with the entire ROS ecosystem. Okay, now the question is, great, so what's next? And Olivier is going to tell us something quite interesting we've been cooking for some times, right?
Yeah.
Regions.
Yeah.
So tell us a little bit more about regions.
Yeah, so I will tell you about Zenoh regions.
But I'll let you go through.
Yeah. And so before that, so let's look at what is the current topology support by Zenoh. So you may have seen this kind of drawings on the Zenoh website or in presentations. So typically we can have routed communication model, brokered communication model, peer-to-peer, as well as mesh, which is basically routed communication, but in a subsystem. Okay, so this is already pretty versatile, but it may be further improved, and we can. It has some limitations that we can overcome. So what are those limitations? So the main limitation is that you can only build 2 or maybe 3 layers of system. And in the first layer, you have no choice but to use the routed communication model, which has its pros and cons. And if you use 3 layers, you can only use brokered communication at the bottom. So you are limited in the way you want to organize your wide system if you want to deploy a wide system. And also, each of those regions have their own limitation in terms of scalability. So here I did put some numbers. It depends on your underlying infrastructure, obviously, but they are rough estimates. So stacking those regions, you will get into some limits when building a really wide system.
And by the way, we have customers that are going to deploy thousands of routers, right, across the internet, and those routers will have underneath, so it's huge systems, and we need to equip for that.
Yeah, and this today may be problematic. So let's go into a concrete example. So assume you have vehicles or robots with, let's say, ROS2 and RMW Zenoh in them.
Yeah.
So basically, you have your ROS2 nodes communicating peer-to-peer in peer mode, and you have a Zenoh router for R2X or V2X communication. Okay, and then you want to interconnect those robots to build a swarm of robots or factory floor, whatever.
To teleoperate them, or maybe
Yeah,
that's
and
the meter
let
infrastructure. Yeah.
them interact with each other. So, thanks to the routed communication model, which is also already pretty versatile, you can deploy a star topology or interconnect them directly in a kind of flat model. But those communication will use the link state algorithm, which has a cost that we don't want to pay. And also it has, again, its scalability limitations that you may hit quicker than you would like.
Or we would like,
Yeah.
right? Yeah.
And you can only build a single layer of system on top of those robots. It's a single Zenoh network, which has its problems. So how to improve that? So to do so, let's first look at what those Zenoh router currently do today. It does two things. First, it routes data from router to router. So typically, if it's between router A and router B, and data needs to go from router A to router B, router C in the middle will forward this data. Second thing it does, if there are clients and or peers connected to it forming a local subsystem, the router will route data for this subsystem. It will represent this subsystem in the wide system. And so it will abstract this subsystem to the larger system and abstract this larger system to this subsystem and route data. So let's separate those two roles and give them two different names. So forwarding data from router to router, let's keep calling that routing and being the role of a router. But let's call serving a subsystem being the role of a gateway. So this is a new concept we bring in Zenoh, the Zenoh gateway. So what is
Although this concept was already there.
yeah, it
but
was
uncalled
built
in a way,
in, it
yeah.
was in the code, but it had no name and was not exposed.
Yeah.
And now let's expose it clearly. So a Zenoh gateway is a Zenoh node that has a northbound that is connected to a north region and a southbound connected to a south region. And so by its presence, it will define a border between two regions.
Mhm.
Okay? And it will serve the south region and represent it into the north region, which
Yeah.
is a wider system. Okay? And it will do as the router does today, abstract the south region in the north region and abstract the north region in the south region, route data between them. A Zenoh gateway, like other node, will have a mode, and this mode will define how this gateway will behave in the north region. And so we'll define what is the communication model in the north region. Okay. One gateway can only have a single north region, but may have one or multiple south regions, southbounds and south region. Thus, you can build a hierarchy of regions. And this hierarchy can have as many layers as you wish. And in any of those layers, any region can use the communication model that is more suitable with its pros and cons. And so you can have brokered, routed, or peer-to-peer communication at any level of your system, which gives a lot of freedom. The only constraint being those regions need to be hierarchical.
Yeah. And just to make the parallel between what it means peer-to-peer versus routed versus brokered. So in terms of the communication graph that each of those can support, can you articulate that?
Well, peer-to-peer, in a peer-to-peer region, all nodes need to be connected to every other node in a click topology.
Yeah. So as we see, for
Right.
instance, here on the
middle left.
Yeah,
yes,
exactly.
Every node connects to all other
Yeah.
nodes. Why? In a
The routed, as an example.
routed is a mesh topology. You
As
can
we see there again.
you can have the connectivity or the topology you want in there. Every topology is valid in a routed region, but this is less scalable and has more resource consumption.
Yeah.
Right? Pros and cons. And brokered is where everybody is acting as a client and connected to one and only one at a given time gateway node. You may
Yeah.
have multiple gateway nodes for redundancy and for fault tolerance, but at any given time, every client in this region are connected to one
And
and
so,
only
for
one
instance,
node.
this would be ideal for an R2X scenario, right? When we have robots that potentially are
Yeah,
connected to an infrastructure and would heavily, greatly minimize the amount of meta traffic that we need to go through, because all of a sudden, in terms of routing, that's kind
yeah,
of
and
trivial.
also for the bottom nodes of those kind of topologies, it's far less resource consumption,
Yeah,
and it's also bounded resource consumption. You have only one connection to handle at any given time.
yeah,
So this will not grow.
yeah. Very good.
Okay, so let's go back to example with our vehicles or robots with, let's say, ROS2 and RMW Zenoh. So again, your ROS2 nodes are still deployed in peer mode, communicating peer-to-peer in a subsystem inside the robots, but you also deploy a gateway. And this gateway could be deployed in router mode and use routed communication in a mesh topology in a subsystem of robots, like the router does today. So this wouldn't change much
Yeah.
compared to today. But if you look at the middle of the slide, you could deploy your gateways into peer mode and interconnect them in a peer-to-peer click topology, which will scale far larger and will be less resource
Yeah.
consuming. And
So,
so
for
you can,
instance, yeah,
yeah,
the first one you would use it if you're doing platooning and you have line of sight problem, for
yeah,
instance, right? Yeah. The second one will work, for instance, on a factory floor, in which
yeah.
usually you are all on the same network. You can do peer to peer. Yeah.
And you can deploy
Uh,
more
yeah.
robots into the second zone.
Although, right, if it's a wireless network, I still think that it makes more sense to deploy a Zenoh router, as we've shown several times, on a Zenoh on an access point, either wireless or 4G, and still be routed or
Yeah, but
brokered in
in
that
this
case. Yeah.
case, you could use the third
Brokered.
case,
Yeah.
which is on the right side,
Yeah.
and you would deploy your gateway in client mode and connect your gateway to one router or any Zenoh node that would
Correct. Yeah.
grant you access to the rest of the system.
Yeah.
So, like this, you can build subsystems of robots or vehicles using the communication model you want between the robots, which was not possible before.
And again, the example is robot, but it's in
Yeah.
fact any kind of Zen application.
Any kind
right?
of
Those could
subsystem,
be
right?
medical devices, could
Of
be
course.
handheld, whatever, right? Yeah.
And also what you can do now is now we have those subsystem of robots or devices. You interconnect them with a new layer, a third layer, with again any topology you want. Here I chose routed, but you could be peer-to-peer again, could be brokered. And if it does enough, you can stack another layer and
Yeah.
you have now a complete freedom in the way you want to organize your large Zenoh system. Yeah. And how
So
you want to deploy it.
yeah, so you can just add yet another layer to make it scale even
Yeah.
further, which is
And
which is
at
great.
any layer, you can choose what model you want to use.
Exactly, which is great.
So finally, let's look at.
So, by the way, something else, because I think it's worth mentioning this. We are discussing regions, and oftentimes people tend to have an idea that is something hard coded in a way, but would be good to explain that in fact we took the deliberate choice, right, to support also some mobility use case.
Yeah. So
Yeah.
when we started talking about regional routing and introducing this concept in Zenoh, we had two main path,
Yeah.
main direction to go, and typically you could tag your peers with a region tag and say, okay, this is region one, name them and so on. The problem with that is now you are tagged with a region. You cannot move to another region easily because you're tagged.
And again, that's not just mobility. We have user, right, that have bigger device with a smaller device that compose the bigger part, and the smaller device can be plugged in one or the other. And so in that case, you would have to know, which region am I now? So it would be a configuration nightmare, right?
Yeah. So that's why we went to the gateway model. So basically, it's where you connect that defines in which region you are.
Yeah.
Okay. Then it doesn't prevent you to eventually name your regions, but you would get the name of your region when connecting or something like that, right?
And so I want to discuss something else with you, because there is another element that we have kind of paused, waiting to finalize this before rolling it out, which is another requirement that we support already to some extent, but we'll want to generalize with this, which is the ability of exposing different prefixes or potentially even renaming the resource across region boundaries.
Yeah.
So do you want to?
Well, eventually, so I think there are multiple cases where we want to do some transformation of the data or of the metadata or
the key expression,
downsampling, filtering, whatever. But the problem has always been which point is the system does that, right? In a completely distributed system, it's kind of hard to define that. Now, the gateway is an obvious place. Right? It's an obvious place to do this kind of transformations. So it could apply to namespacing, downsampling, and so on. Yeah. So finally, so how to configure those? So this is work in progress. This is not completely defined yet, but basically, Zenoh Gateway is a classic Zenoh node with the same configuration as other nodes, but it has an extra entry in the configuration, the gateway entry, and in this entry you filter out what connection goes to the southbound, and what goes to the northbound. And you define that by filtering them through network interface, mode, Zenoh ID, username, whatever would be suitable for that. Okay. So let's take two examples. So typically in a robot, what you could say is everything connecting through the Wi-Fi goes to the northbound because it's V2X or R2X.
Yeah.
And everything connecting from the loopback, it will be northbound and create a local subsystem. Southbound and create a local subsystem. So yeah. Another example would be everything that connects as a peer, every peer will go to the southbound and will create a subsystem of peers, and every router will go to the northbound. And basically, if you do so, you have the current router, which does that today. But then you can filter on other things like usernames, Zenoh ID, certificates, whatever. So I think this will bring a lot more freedom in how you can deploy your Zenoh system and a lot more scalability.
So essentially, let's discuss a bit scalability. There are multiple aspects. So that will mean that we are now able to tune the configuration to further reduce the meta information that needs to circulate.
Yes.
Because all of a sudden, if you don't need to do link state, well, just don't, right? Because that has an overhead. And so I think that's one point. That will impact potentially the system startup in some situation, right? Which is also important. Memory utilization, CPU utilization. So there are lots of aspects that will be improved. So this is why we decided to provide a sneak peek, because this feature is quite massive. So obviously what they're asking is, when can I get it, right?
Well, this is in progress. Well, we have something that is basically working. So I would say the core is mainly done thanks to Mahmoud. Mahmoud is doing everything.
So come Mahmoud. Don't hide.
But like always, the demon is in the details. So there are a lot of little things to
refine.
But we hope we can get this early next year, in few months.
Yeah. And I think pressure. I think we'll try to get it out perhaps as on a branch. We'll ask the community to test, right? Or maybe we'll just drop it in main, ask to test, and eventually decide in which release it will get.
Because another point is that we hope we can make this fully compatible with the current version. So if we can manage to do that,
then it will be earlier.
We can deliver it earlier.
Okay, cool.
Right now, we're mainly thinking about how to make the configuration nice to use and as
user-friendly
as possible, and not too error prone. And then once we have a good story for that, then it will be
okay. Cool. We'll be ready to be tested by you guys. So I'm looking forward to it. Okay, great. Thank you, guys.
Welcome.
And we are going way too fast because but anyway. So, often the question is, how can I help? Well, first of all, if you want to get involved and contribute, the place to go is Discord. You have the QR code there, so flash it and join Discord. If you're not there, you're welcome to to join. And we're always welcoming, obviously, with contributors, and so on and so forth. Then obviously your company can also help funding roadmap items, which is great. And we have had this year, it's unfortunate I cannot name the company because of non-disclosure agreement, but I think there were few companies that funded some key extension in Zenoh. So thank you very much for that. You can help doing even more cool stuff on this pretty interesting technology. Then obviously you can reach out if you need consulting, any kind of commercial support, just contact us. That's pretty straightforward. And then, by the way, guys, if we are here, as I always say, it's not because of us, right? But it's because of them. Because in the end, that's the reality. And actually, I found today on my desk an haiku that apparently was written by Zenoh. So I was asked to put it on the slide, so I did, right? So, that's how it reads: "Dragon forged in code by many hands and keen minds. Together we fly." And that's the message that he asked me to share with the community. So again, thank you, because we all put our contribution. You put your own contribution, and we are growing, bigger and bigger. That's breathtaking in a way, right? Because it's been an incredible journey. And as per tradition, there has to be a little surprise, right? Otherwise, it's not the Zenoh user meeting. So, what is the little surprise? You can read, so you shouldn't say. The little surprise is that we have started cooking Zenoh 2.0. Okay, and we plan to release Zenoh 2.0 second half of 2026. So first of all, stay tuned. And now you understand that the discussion we're having on regionalization also impact, whether we will have to wait for 2.0 or we'll be able to roll it out before. Our preference is to roll it out before and make it completely wide interoperable. And then if there is anything further optimization we need to tweak, we can do in 2.0. And so what I would like to do, whether you are joining in on LinkedIn, on YouTube, or Twitter, just please put your wishes for 2.0, okay? And I will ask you to do this. So, Julien, what is your wish for 2.0?
Well, I'm thinking about something around shared memory, right?
Yeah.
I think that we can do a lot of optimization.
Come closer. So yeah.
We can do a lot of optimization in shared memory with regard to all the discovery, because we know already that in robotic, all the discovery of the graph cache made by ROS2 is quite a burden at startup. If we do everything in shared memory, that will simplify and accelerate the startup time for a big robot system.
For huge, because we're already serving big, it will be like instantaneous. But that will be terrific, absolutely.
That will be very cool.
Mahmoud, what is your wish? You guys keep thinking, okay? Because I'm going to ask everyone.
My wish for
2.0
would be an improved configuration system, for example.
Yeah, I agree with that.
Because there are builders in the API, to have a published schema, maybe some more validation to help root out configuration errors.
Yeah.
I think that's
because the JSON 5 API, it's error prone. I think everyone, I've done my own typed API on top of that. I think every user probably does it, right? Yeah. Usama.
My wish for 2.0 is...
I'm not sure they can hear you, so get a little bit closer.
My wish for 2.0 is mutual authentication for user password, and user password that doesn't require knowledge of the clear text password.
Correct, on the router. Yeah.
So there have been users who have had issues with ACL when using user password because of the fact that it's in only one direction. So I think some people would really love this.
Yeah.
I myself would really love this.
Cool. Yeah. Sasha, how about you?
So my wish, not only for 2.0, but in general, first of all, I would like to have regionalization in.
Yeah.
It's my main wish, but in terms of some small changes, which small for change, but will break some stuff for many users, it's changing our admin space to have more efficient format.
Yeah.
To not have a JSON, because even
so binary serialization
yes,
format. Yeah.
Even now we have a huge amount of data, and as soon as we will working with thousands of routers, the amount of data on the admin space will be
and we absolutely
much
need to
huge, yeah.
we absolutely need to
somehow
address
optimize
that.
it.
Yeah.
Yes. It's small change, but it will break
and again,
current protocols.
Yeah, one approach that we often discuss is yes, compress, but compression takes CPU, right? So yeah, having a more efficient wire format for admin will be a big plus. Yeah, absolutely. Olivier.
Yeah, so what I would love to have in the 2.0 is what we call here ZID-based routing.
Yeah.
So
okay, so that's an interesting one. We can talk half an hour about that.
Well, so yeah, so Zenoh is a form of content-centric networking, right?
Yeah.
You name your data and you
route by name.
You name what you want to subscribe to. You name what you are querying. You use name that names the data itself, and you are completely location agnostic.
Absolutely.
Right?
Yeah.
But sometimes it's bad to be too
agnostic.
Yeah. Like in Zenoh, where there is no pub sub only or no query reply only. Sometimes you need both.
Yeah.
Both. And again, I think here sometimes a bit of host-centric, or in Zenoh case,
I mean, if I need to talk to you, I really need to talk to you.
Yeah,
right?
A bit of node-centric communication sometimes is helpful. And typically, I want to talk to this node, or I want to access this node, and Zenoh locally knows where the node is, obviously, and even in a wider network, will perhaps more easily route to some node than to some data name, right? So adding the possibility to pub/sub and to query some given Zenoh nodes with the ZID as the identifier would be really good. And that would help for the admin space, because admin space are from nodes, the Zenoh nodes themselves, infrastructure or application nodes. So you can add the admin space more efficiently, and it could help doing different query mechanisms.
A different query mechanism, which I think is worth expanding, because today, so as you mentioned, Zenoh is name-centric, so we route using names. But when we do a query, gods know where we end up. And then we have to find the way back for the data to reach the source of the query. Mm-hmm. And for that, like in the famous tale, we drop breadcrumbs. Yeah. But breadcrumbs is state, right? And this state has to be cleaned up. And if a query takes 5 days, because there are some applications, I'm exaggerating, don't take 5 days, but so that can create some issue. And a node-based, in that case, routing on the way to the source of the query would be quite interesting too, right?
Would it be stateless in the infrastructure itself?
Exactly. Yeah. Then we wouldn't be able to do consolidation, as you mentioned.
Yeah, it has pros and cons, like everything.
But it's a good additional mechanism.
Being able to decide which model you want is always good, I believe.
Yeah. So. Mikhail, how about you?
What I'm really dream of is what we will have no STD Zenoh in browser. It will be super efficient because Rust is native for Wasm, and there is no reason to not have native Zenoh in the browser.
You are absolutely right. And in fact, talking about that, I want to do 2 things for the community.
And
go ahead.
One more improvement. We have Zenoh C. We have a lot of mapping to different languages, and all of them made in kind of different ways. They evolved, but it's possible to make common API and build language bindings based on common API. So there are some directions into this.
Yeah, absolutely. Thank you. And by the way, I actually had forgotten something quite important that we have just announced. Thank you. You reminded me, right? So there was a big miss on my slides. But indeed, the other things that we dropped and announced at the ROSCON this year was Zenoh Rust Bare Metal. So now you have an implementation of Zenoh which as of today, I believe supports all of the primitive, so pub, sub, and query, and is bare metal. The project is evolving quite quickly. The performance are outrageous, so you're welcome to test it, and that's on Zetascale website. And now, obviously, I won't spare myself from commenting. So as you guys know, one of the things that I would like to look at is the support for large messages, especially making sure that we can have optimal end-to-end latency for very large messages, and that would require some modification on how we do fragmentation. So perhaps that's something also we'll be looking at. But again, we are looking forward to hear your wishes, and once we'll have finalized ours, we'll announce the roadmap and a better timeline on when we plan to drop the 2.0. Okay, so at this point, I think we can officially start the Zoom 2.0. We are a little bit ahead of schedule, but I saw that we already have some speaker online, so we might take advantage of that. So just give me one moment to bring the speaker on, and we'll keep going. Okay. So, David, can you hear me? So actually, I mean, as we're already here and we are ahead of schedule, do you want 20 extra minutes? Or let's say 10 extra minutes?
I'll take a few minutes. We'll take a bit of time, and we can talk a bit about some of the things that we're doing.
I don't see Oron yet online, so if you're happy to go, I would say let's go. Let's keep it rocking.
I'm ready to go. So I was going to talk a bit about PicoROS, which is built.
Sorry, David, do you mind sharing your screen? Because
Sure.
that way I make it stream too. Yeah.
Okay, here we go.
Okay, great.
Okay, here we go. PicoROS, Zenoh.
So a second, because I see it's looking all black for me.
It's looking all black for you?
It's coming? Oh, here it is. Okay, great.
Okay.
Ready to go.
Robots, PicoROS, and Zenoh, and I'm going to switch between this and some of the other images that we have. I'm in my lab at the moment. So just, a little bit about Ubiquity Robotics. Our goal is to go from a state where building mobile robots was pretty difficult to robots were everywhere, enabled by robust standard components. Of course, if you want to have robust standard components, you need robust standards, and Zenoh is part of the standard tool set that we use. We've built many custom robots. Here are some of the examples. I'm going to switch out of my, at the risk of causing problems, I'm going to switch out of my mode, and you can see some of the robots that we have around me, various different kinds. Can everybody see all of the robots that I'm surrounded with here? Okay. And we build robots, everything from this sort of size here all the way to robots that are that sort of size down there. Now, as somebody that likes to build robots, and is a group of people that like to build robots, as I mentioned, what we want to try to do is work with robust standard components. We've built from the very beginning. Whoa, hold on. From the very beginning, we've always worked with ROS. And today, the information transport is done with Zenoh. We've worked with ROS since 2012. But we want to have a robust standard platform, because ideally what we want to do when we build a robot is we'd like to have most of the elements of the robot be standardized, and for us to change just a few elements. So this image here is a sort of typical architecture diagram that you might find on one of our robots. We're going to have a computer with robot management tools, pub sub, middleware, operating system, and you're going to have a little bit of payload code that is going to really define the application. All of our robots have motor controllers. They almost all have nav sensors. And typically our robots will have some kind of payload sensor, something that is particular to one application or another. And the goal is really to try to change as little as possible to minimize the amount of work. That way we can get the benefits of a small focused team, and our value add is maximized. Now, the ideal architecture really has certain qualities. If we think about the properties of blocks in an architecture, what we really want them to be is hermetic, where no functionality escapes except through the interface. We want it to be atomic, testable. We want the architecture itself to be orthogonal, where each part of the architecture has a different purpose to every other part, and we want it to be really scalable. Today, or pre-Zenoh, should we say, we always had a problem that every time we put on an additional peripheral, you almost always had to put some sensor driver, nav sensor driver, motor driver, some additional component on the computer. And these sort of blocks would often interact with each other. They'd often create problems, and you get driver hell. This is where, and I think most of the people online will be familiar with this problem. And it really comes down to the fact that your interface is non-hermetic, that you're allowing other things to slip through your interface that aren't related to the actual functionality of what you're trying to do. And we didn't want that. What we wanted to do was move to a world where the interface fully defined the features of whatever it is that you were connecting together. And so what we did was leveraged Pico Zenoh to create what we're calling Pico ROS. Pico ROS is essentially Pico Zenoh with a few extra bits on it to define the ROS elements of that. And what that enables us to do is we can put Pico ROS on a microcontroller that may sit on our payload sensor or on a nav sensor or on a motor controller. And then you can start to talk directly to the motor controller using Zenoh messages in an entirely, without requiring any sort of bridging or any other little element in there. You just simply allows you to communicate directly with these elements. And that prevents the need for drivers and prevents driver hell. And it's now available, free and open source. I'll just jump to that. This is the GitHub for those that are interested. And what we're going to do is release a set of Pico ROS / Zenoh hardware to enable this. So data interconnects, it will have a Zenoh router on it. We're collaborating with Zetascale to build this. We already have various motor controllers that are available, and we are going to release a series of sensors. We're also working with other sensor makers globally to try to get them to add Pico ROS onto their hardware. Now, the effect that this will have is that you should be able to plug your hardware elements together, and without having to add drivers, without having to configure, your ROS topics should come up. You should be able to see what is there, and you should start to really get into the business of developing your system. So we've also got a brief demo here. So I'm going to exit my screen. And
so here we are.
Julian, we've got a robot right here.
Yeah.
So just to give a bit of context, maybe Julian, you could get it to wiggle, but while you're setting up on your end, I'll explain, just get it to do what we have. Yeah. What we have in this robot. So what you see in this robot is, this is a robot that we developed, and this is the electronics that's inside it. If we sort of look at the electronics here, this is the motor controller. I showed you an image of it in the previous slide. And you have a microcontroller on that motor controller, as you would expect. That microcontroller is running Pico ROS on it, which is of course enabled with Pico Zenoh. So that's running right on the motor controller itself, and publishes command vel messages directly into the rest of your ROS system, and is visible in a normal way. There's no driver that I need. There's no anything like that I need. And what we've actually done with this motor controller is we've connected it to. So I'm sitting in my lab in Slovenia. We've connected this to a router, which is, I believe, in Germany somewhere, and
Hamburg,
Frankfurt. And Julian's got a joystick there, which is again enabled with Pico ROS, has a microcontroller on its ESP32 sort of standard kind of thing. And Julian, if you could please do the honors of trying to drive the robot around from France.
So I'm plugging the power in the ESP32. It's directly connecting to the Wi-Fi, and now I can move the robot.
No latency.
Oh, going too far.
It's okay. It's right over here.
Going too far. I'm a pro driver. Sorry.
So,
no, but the video has more latency than what we have in Zenoh.
Yes, it's hard to get exactly where I'm moving because of the video latency, the streaming latency, indeed. But if I just turning a little bit around,
so next year we will have to stream on Zenoh, guys.
It's all right, Julian. I was sitting there driving this big robot in just a few minutes ago and managed to completely destroy a cupboard as I drove it in. So you don't have to worry about that sort of thing, right? Believe me, make a mistake with the big robot, it's a lot more dangerous than this little guy. So yeah, all right.
I'm ready.
Go back.
So and I think this just shows what you can do, right? I mean, add a simple additional layer. This is, we've implemented this on STM32 microcontrollers. You can implement it on a wide variety of microcontrollers. We've tried to design it to be microcontroller agnostic. And like I say, where we think the world should go is everyone should put Pico ROS on their sensors or their motor controllers. They should all plug into a central piece of hardware, which will be enabled with Zenoh, with the Zenoh router. Plug all those items together. The ROS topics simply come up without having to require configuration. ROS does a really good job of standardizing the message type. So
yeah, exactly.
As long as and really that's all that you need. You don't want to have an a message type that comes from, say, a LiDAR coming in and going into a driver, having to require some conversion, having to require CPU cycles. So our vision is that all of those messages should be transported on Zenoh, and it should work from the lowest level all the way up to the highest level. We are,
the parallel thinking.
We're building that. So we're building all of that structure, and then we're also enabling that with a fleet manager that also will be Zenoh based. So we're taking a derivative of OpenRMF. So putting some additional user interface features on it, and so you're going to have a Zenoh based infrastructure right from the motor controller all the way to your fleet manager. Right. So yeah.
Cool.
Okay. Any questions from anyone?
Okay, thank you very much, Eric. And in fact, a few weeks ago, I was thinking back in the days when we used to have VESA. You recall the VESA bus?
Yeah, of course.
Right. In VESA, when you had to plug a new card, you needed to configure the interrupt. Otherwise, there would be a conflict, right? Then we had COM, and there was some level of plug and play. And I think it's interesting because on a robot, you cannot have an hardware bus that you plug everything because there are so many different kinds of I/O. And so what you are doing, it sounds like providing a software bus that in a way solved the same problem that to some extent was solved, right, in PC by COM, to make plug and play hardware, right, with common bus And that's pretty cool. But I think the benefit could be precisely the same. Yeah.
Right. And you can see that people have tried to solve this problem in computing. I mean, the advent of PostScript, define how you should talk to a printer, all of these sorts of things. You have to fully define your messages from OSI or for the complete stack, from OSI 1 to 7. So the point is that that's necessary to do. Now, ROS handles a huge portion of that, because you've got clearly defined message types which have standard formats and so forth. The lower level layers are often handled really well by Zenoh, and the great thing is that it works from the microcontroller all the way up to large big iron systems. So the point is that you really want one method for everything to talk to each other. And you don't want to have to spend your time. When we're building custom robots of many different types, we don't want to have to spend our time wrangling different drivers, trying to make sure that they fit into the compute budget and so forth. And this can really take all of that away, because any compute budget that there is sits on the microcontroller, because it correctly presents the data to all of the other layers without requiring some interconnect. And our data interconnect system, I don't know if you caught it, it was on the slide, but that's going to support Ethernet, it's going to support serial, it's going to support various different kinds of serial, so RS422 and CAN and things like this. So the goal there is that you can plug whatever kind of
physical layer
into it, and then you can worry about your application and how you provide value to the customer, and you're not spending your time worrying about, does the driver work? Is the LiDAR is the LiDAR driver arguing with the sonar driver? And that's really the goal. And we can spend more time thinking about the application and the consequences of that. So that's kind of the direction that we're going. We're very excited by it. We are building out our 6th generation robot platform design. And again, that platform design will support everything from small robots like this all the way up to big robots like the one behind me, and everything in between, things like those robots up there. And we're going to sell the robots, we're going to sell the base robots, we're also going to sell the peripherals. So if people want to buy motor controllers from us that have Pico ROS on them that you can plug in and make work, those will all be available as well.
Okay, thank you very much, Dave. I mean, I think your initiative can really disrupt the market, because all of a sudden, even in terms of sensor provider, right, they don't need to invent a new way to communicate. Everything is standardized, and they can focus on making their job. Even in terms of replacing sensor, I mean, they would completely add a level of agility that is, we have not seen so far in robotics.
Yeah, and we want to have it an open ecosystem. We're going to build. I think Ubiquity Robotics, we're planning on building a sonar, we're planning on building a radar. But what we want to do is invite other sensor makers to come and be in this path with us, so that we can all be using Pico ROS based sensors together. That's really the goal here. We want to, and that's why it's open. Everything's open source. So that's what matters for us.
Okay, great. Hey, David, thank you very much. Great presentation. Great work, right? And let me hold on, because what I will do, I will bring Aaron on, so we'll have a good segue. Hey, Aaron, can you hear me?
Yeah, I can hear you guys.
Okay, very good. So, David, thank you very much again.
You're welcome. Thanks so much.
Yeah, take care.
Bye.
Okay, Aaron. So it's your turn. Ready?
All right. Yeah. Sorry, I didn't join early to figure out the timing.
No problem at all. Do you mind sharing your screen so I can make sure that everything is in place, and we'll get going?
Let me try.
And Aaron will be talking about Zenoh using OpenRMF. We just mentioned OpenRMF 5 minutes ago, by the way.
Yeah, when I saw that David was also going to speak, I knew that it was going to be involved in that as well. Yeah.
Okay, look, let me bring up your screen, and you are good to go. Let's go. The floor is yours, Aaron.
All right.
Please introduce yourself. real quickly, and then we keep going.
Yep. Hi, everybody. My name is Aaron. I'm a software engineer at Intrinsic, and at the same time, I'm also a PMC member of OpenRMF under the OSRA, which some folks would know it more as an Open Robotics Foundation, Open Source Robotics Foundation. So today I'll be talking a little bit more about OpenRMF and how we've been using Zenoh. And specifically, it is what we call Free Fleet, how we have actually been using this integration. Let's see. What we'll go through today. So I'll do a quick introduction to OpenRMF for folks who don't know too much about it. I'll try to do it really quickly because I know that folks may have heard about it just now as well. How we are integrating with OpenRMF using Free Fleet and how Zenoh's involved with it. I'll show a quick demo. It's not going to be live, but there will be a bit of a demo on how it actually works. And then I would also talk a little bit more about how we've been, the few key things about Zenoh that enabled us to do certain things throughout the OpenRMF ecosystem. And then what's next, essentially, with Free Fleet. So first things, quick introduction to OpenRMF. Some folks may not know what this is about, but this is essentially a GIF that you'd see if you had gone to the simulation demos of OpenRMF. This is an airport world where we had robots running around, avoiding each other and doing things. So I am repurposing some of the slides that we use normally to explain what OpenRMF is. It is a framework and a collection of libraries that allow us to deploy robots in an interoperable way, such that we could have robots with different vendors working with each other, as well as interact with facilities and whatnot. This is to actually solve a problem where we are getting to the point where individual robots are now smart enough that they can do their jobs amazingly. But what we want to do is to put them all together and cooperate in a single facility. And this is also an effort for people to not be locked into vendors and actually be able to scale their fleet of robots to do exactly what they would like to do with their facilities. Let's see. So as I mentioned, OpenRMF is a collection of libraries, packages, and a set of standards that we use to communicate with a lot of robots as well as infrastructure. This is one such example of what RMF does, which is to manage multiple fleets of heterogeneous robots and then handle all the traffic conflicts and negotiation in a navigation graph sort of way. This is just one of the examples that we have in simulation. And one such thing in this suite of libraries is that we allow people to build up their worlds, draw up their navigation graphs, and this would allow them to test things with doors, with lifts, throughout multiple floors, and get different interactions out of the robots they would like to test with the different behaviors. So how does RMF actually look like from an architectural point of view? So we have in the middle a bunch of core libraries, and on both ends, left and right, there are ways for different pieces of the puzzle to integrate and to actually talk and, I guess, reason with each other on how things should be done. And for example, the key things that we'll be focusing on is actually mobile robots. So we have this concept of fleet adapters where as long as the OpenRMF deployment is up, what users just need to do is to spin up their implementation of a fleet adapter that manages their fleet of robots, and that would already immediately start working with existing robots that have been integrated into the deployment of OpenRMF. So more specifically, we'll be talking about how we've been doing it with Free Fleet, and this is essentially Free Fleet was an effort for us to pipe in individual robots that people have been developing and working on. And in particular, we are targeting the open source nav stacks, essentially nav1 and nav2. So how it works, this is also a high-level overview on like how Free Fleet looks like. So on the left side, we have the Free Fleet adapter, which is one of the fleet adapters that manages robots but talks with other fleets as well as talks with the rest of OpenRMF. And on the right side, we have folks who perhaps have a couple of robots that may have come up from their the labs where they have been testing certain algorithms and whatnot, and they've been using like nav2 or nav1. So the first thing that we do in this integration is that we introduce the Zenoh Bridge ROS2 DDS. So using these, we drop it into each of the robots and we apply namespaces as well as filters, filters, and figure out like what needs to be rate limited and whatnot. This would allow us to have a much better integration experience like down the path, as I would explain in a bit. So on the right side, you see that after what the Zenoh Bridge would listen to would be the TFs, or as well as the ROS2 actions of like navigate to pose, for example. And what we'll do next is we'll have a central router for the Free Fleet adapter, which the Free Fleet adapter would talk to the router using pure Zenoh messages, essentially. So this is actually doable precisely because the way the Zenoh Bridge ROS2 DDS mangles the topics and messages and performs the serialization and deserialization in a rather standardized way, such that we can actually do it on our end and just work directly with the Zenoh messages themselves. So there is, we also support, like with this architecture, it's also possible to skip the router itself and then just do everything peer-to-peer, but then it's less reliable, and we have verified this like with hardware as well. One of the, precisely because of how we're doing this, we also support a rather weird way of integrating, which is if, and this is actually something that robot people that work with nav2 would do sometimes as well. They would already namespace their robots. Perhaps they are on the same network and whatnot, and they don't want to interfere with each other. So if they have already namespaced their robots, we just use a non-namespace bridge and then would work with it exactly the same way from the Free Fleet adapter side. Yeah, so I'll be showing like a couple of GIFs, which are actually part of our example repositories from Free Fleet. So over here, we just spun up the basic nav2 stack with a couple with a turtle watt, and then right now on the right side of the terminal, we're just launching all the different things, and this is just the web UI of OpenRMF, and we are able to send the RMF-related tasks down and then control the sim robot that's running nav2 down. So the other example that we also have in the example repository is that we run the, I think they call it the unique multi-turtlebot example in nav2, where they basically spin up two namespace turtlebots, and then we allow, in the example, we just spin up the non-namespace DDS bridge, and then we just integrate RMF into it as per normal. So one Free Fleet adapter can handle like multiple robots, and it's always good to be able to test in simulation as well. Yeah, so in this particular case, using RMF, we are able to send a task, and then it would find which robot is the best suited to do this particular path planning, to do this particular patrol task, and then it would dispatch them. And then in this GIF, we'd also see them sort of like avoid each other and on a high level point of view to get around each other. Yeah. Yeah, so that's like some of the examples that we have, some of the simulation examples that we have for people to try out of the box on for Free Fleet and OpenRMF. Some of the other notable users that we are of Zenoh in this particular integration. One thing that we enjoyed using it with is to do testing. So because we have been using this architecture of using the Zenoh bridges, which means that we are just dropping it onto any standard nav2 robot, and then allowing the bridge and the Zenoh namespaces and the key expressions to handle all the integration work. We'll be able to do it in a rather Dockerized way and such that we can do like integration testing nightly and all that to make sure that nothing is broken. Like this is a Docker compose file that we have upstream. So this is a Docker image that we just built nightly that sets up the nav2 robot. And then we have an image that sets up the Zenoh bridge with the proper configurations and a specific domain ID. And then we have another router. And then in the workflow, we just spin up Docker Compose, and then we run all the ROS2 related tests that we need, and then we can stop the container. So that was a really, we found that this has allowed us to, at the very least, write code and be at least very sure that something is not, if something is working or something is broken upstream, essentially. The other one that we found while doing hardware testing was that we had middleware issues with the Turtlebot 4, and it's actually because of it comes with a lot of, it's quite tricky because of the hardware setup that Turtlebot 4 uses. So it has both the Raspberry Pi, the Create tree, and then we have the user PC. There are two different topologies depending on whether or not you set up simple discovery or not. But essentially, out of the box, users are, at least out of the box, it's expected to use very different like DDS configs on all three components just to make everything talk to each other. And you can spin up the navigation 2 stack. But there's been like quite a lot of people having a lot of issues, and I think this is one of the weaker points about DDS-based RMWs, because we rely, it can do so much, but users actually need to configure a lot of things to have the most optimal performance. And one thing that we did to sort of resolve it was that we just remove all the configs for DDS, use Cyclone everywhere, and then we just threw in another bridge, essentially. And then we added another bridge on the user PC so that we can just start working with RMW Cyclone DDS on the user's end. So that allowed us to do at least some amount of hardware testing without any issues on. We found that this worked best with like various different network configurations. So what's next? We are considering like moving to RMW Zenoh CDP now that a lot of things have stabilized, and we see the benefit of using ROS2 directly and managing everything via namespaces or ACLs using the either the router or the session configs. So this there's actually a conversation or a discussion ongoing online. Some more information can be found here with the link. Yeah, so we also have to consider the out-of-the-box experience with existing nav2 robots. We can't just make sure, like, if folks are deploying using this method and then we change everything, that might be tricky as well. Some more notes and links. There's a link to the discussion where we talked about like RMW Zenoh CPP, and then some links about the Zenoh Turtlebot 4, and some more links about OpenRMF in general. Yeah. So yeah, that's it for my sharing session. Like I'd be happy to open up the floor for any questions.
Okay, thank you very much, Aaron. Oh, yeah. Can you hear me? Yeah, very nice talk. So I have myself a question, and then let's see if So you started using the Zenoh bridge, right? Which is a path that that was the typical path for pre-RMW, and now you're migrating to RMW. You still see the need to having interoperability between Zenoh RMW and the bridge, because this is something that we have been requested a few times, and I was wondering, whether that's something that would be useful, you guys see as useful or nice to have.
Do you mean interoperability? Oh, so interoperability between RMW Zenoh itself with the bridge plugin.
Correct. Yeah.
So in a sense, having a bridge between RMW Cyclone and RMW Zenoh.
Zenoh, exactly. Yeah.
Oh, I personally do not know what would be the best case scenario. One thing that we did note is that a lot of robots. Okay, I'm more specifically talking about total bots themselves. A lot of them don't come with RMW Zenoh setup, so that's why like Cyclone was the way to go for me. With regards to piping it to Zenoh itself, I think if we have a case where OpenRMF can benefit greatly from using RMW Zenoh, like very specifically, we are using RMW Zenoh for its features to get the most performance for OpenRMF, then there would be a case where I think the bridge between a different like Cycle and Zenoh would actually make sense. But that would be
I mean, maybe I was
hardware level. Yeah.
Was more about having robots, right? That you can't necessarily update the version of ROS. Yeah, we could still build a Zenoh RMW, but would be easier probably to have just a bridge on the robot, right? It's incremental solution as opposed to.
Yeah, that's for me. That would be the only use case. But still, you will need to be careful to stay in the same ROS distribution.
Absolutely,
right?
yeah.
Because from distribution to another distribution, the package can change the type formats and so on.
Yeah. So let me check if we have any question from the community. And by the way, please recall that we have a constant view of the question. We are answering in real time. So if you have questions for the speaker, we'll relay those. Any question from you, Julian, or from any of you guys? No. So, Oron, thank you very much for your. Well, I called you the Norwegian way because I lived in Norway for some time, and double A is O.
Oh,
and sometimes it's A. So technically,
Gotcha.
Norwegian is Oron because it's a Scandinavian name, right? But sorry for that. Okay, let me bring Edgar online, and we'll greet him, and then I'll let you go. Sure. Edgar, hello, how are you?
Hey, hello.
Oh, beautiful Christmas tree. I mean, we were discussing that this year we actually forgot to make it because every year we've had the Christmas tree in the office and we forgot this year, so we won't have any gift. Yeah, because otherwise we won't have any gift, right?
We still have a few days.
Yeah, indeed.
That's why I brought one.
Yeah, great. Oron, it was a pleasure. Thank you again for joining Zoom 2025. Ciao.
Bye, Aaron.
Thank you. Bye.
Okay, so Edgar, I'll bring your screen up.
Yeah.
Your screen is there, and the floor is yours.
Okay.
Ciao.
Thank you.
Enjoy. Yeah.
Yeah. So, hello everyone. I'm Edgar Riva. So I work at Bonsai Robotics. Thank you, the Zenoh team, for inviting here. So, just a quick introduction. So, as I said, we work at Bonsai. Bonsai Robotics is a company in the farming, agtech farming industry, interested in autonomy for farming and outdoor applications. So I'm part of the kind of new refreshed research team. I'm gonna give some details about that. And this talk is gonna be more about how we use Zenoh with Rust and all the other supported languages on the more, let's say, research side and the platforms that we use for research. Here. So Bonsai has several products, and the Amiga tractor is one of them. So to give a bit of context here, this summer, Bonsai, so originally the Amiga was developed by Farm&G, the company we were working for, and this summer we recently merged companies, And we luckily continue working on the Amiga. So we've been building this a platform for already 3-4 years, and basically it's a electric tractor, we want to call it, for specifically for farming, but it can be used for other applications. And as I said, it's electric, it's lightweight, modular. You're going to see now, but also the good thing is that the software is we have an SDK that it's open source, that it allows to many people, not only companies, individuals, but research labs to perform different basically types of research. So, well, I already mentioned some of the capabilities: open source, configurable, modular. So modular also in terms of hardware means that we can just replace parts, that remove sensors, made it wider because all the, the different farms, crop fields, they are different sizes, shapes. So we found that in this kind of architecture for the hardware was very beneficial for all the users. And so this was it's the platform. As I said, the Amiga was started even before that, 2023, but there was an evolution these last couple of years, especially the Amiga V6, the V6 Plus, and actually this September we released 2 new models and more to come. The Amiga Flex and the Amiga Max, which is something like much bigger for large, let's say, large-scale crops. But the idea is that all of them, they share kind of the same architecture in terms of both software and hardware. So let me go to the next one. So as I said, this summer we met companies, and one of the results of that is that Bonsai already, so he's already selling a stack for automation that you can integrate in tractors, etc. But yes, all this is cool. They are, it's working, but we are seeing like that there is a different approach, right? Probably you all heard about the advance of these visual language action models, generative AI, etc. So as a result of the merge of the company, we created a different division in the company. We call it the end-to-end lab. So basically, we do exploration of in a kind of open research kind of framework for farming, outdoor logistics, to research in the BLM, BLAs, and then recently I'm going to show now a use case for the simulation, how we are starting to leverage simulated data for training these models. So here, this is the kind of architecture we have today on the research we're doing, and it's where we leverage Zenoh. So also, I want to mention that since the summer, we started kind of a revamp of all the software for the robots. We tried different frameworks, and we finally chose Zenoh in Rust. So all robots, the HAL layer, it's Rust, and all the sensors, the drivers, it's Rust. And then we added the layer of Zenoh so that we can easily communicate. Especially, we chose Zenoh in the first place because it has a multi-language support. And here is one of the examples that we use at research, but other teams, they are leveraging that. So this means that we have the robots that they all stream in Zenoh, and then we can just write apps or different integrations using different languages from Rust, Python, TypeScript. Now I'm going to show in C++ how we integrated Zenoh inside Unreal Engine. So as you can see here, so for the research, what we're trying to do is from the simulator, we created on top of Unreal I don't know if you're aware about the Carla simulator. So we started kind of in this direction. So we wanted to use Unreal to basically model different farms, different, I don't know, let's say behaviors. And we wanted to talk, we wanted to make something that whatever we do in simulation, then it's easy for us to translate in the real robot. So basically the exercise here, we created this small plugin on top of Unreal C++ that we have, this is new from last week. We have deployed that in Google Cloud. So we have in Google Cloud this instance running Unreal in C++ that we are exposing. So we have modeled basically the HAL layer seamless to the real robot. And we are exposing all the topics in ProtoWAF. We are using ProtoWAF. So we are exposing everything over Zenoh. And the cool thing is that we created this sort of ecosystem of, for example, we have a TeleOp app that through Python, there is a Python backend with a front end in TypeScript that we leverage also Zenoh to do TeleOp. Then we have another component that is the recorder that is just basically subscribing to everything through Zenoh and then dumping everything to MCAP. We have also an integration with Foxlove that in the same idea. We subscribe from to the Zenoh topics from the Unreal, and then we just stream the data in Foxlove. So yeah, this is the pipeline that we use today for experimenting with the vision language action models to train and gather data for now simulated. I have here, let's see. So this is basically what it looks like, the simulator today. So this in the background is running, as I said, Zenoh. So this is command, I think I have a controller here. I don't know if you see my screen, but I have the Xbox, and this was controlled through a front-end app that was communicating through Zenoh, and then internally the C++ Zenoh layer in Unreal was actually applying all the actions, controllers, etc. Oh, wait, sorry. Oh, sorry, I missed. Okay, so as I said, we decided to go in this direction, Zenoh, because for us it would be easier later to, let's say, try something more on the research side and then apply it in production. So here you didn't notice a lot, but the actual change that I did from the previous slide was here on the inference side, where we had this Xbox controller just sending the commands to the robot, but because we're using this common interface with Zenoh and the same ProtoWAF messages, so now we can, when we train the BLAs, we can just replace that controller and just put our model policy that we train. So the rest of the architecture is the same. So that's one of the benefits I think that Zenoh is bringing to us, that we can just have a very stable basic API of the robot, and then we can just create, in our case, this ecosystem of apps. So I want to show some of the recent results. So this is Unreal rendering at the same time, streaming on Foxlove, and at the same time running the PyTorch inference that is basically sending over Zenoh the canvas, like we're mimicking the canvas commands to Unreal. And here, for example, we just made a small proof of concept, for example, for obstacle avoidance. So we trained this model with gathering the data, basically reading images and the canvas. And we trained this policy, and then at the same time, as I said, just replacing like the manual controller by in that case, the PyTorch model, we can leverage the same architecture. So yeah, here I wanted, just because this is a Zenoh related conversation, so I wanted just to bring some examples. For example, here the Zenoh to Foxglove integration we have. So basically, we have some sort of dispatcher that we are subscribing from the different topics in Zenoh, and then we are just actually we're using a Fume just to basically enqueue all these samples, and then we have a kind of another dispatcher to basically cast all the messages to Foxglove, and that will enable us, for example, to do like a remote also operations to monitor what's happening. The other example I wanted to show how we are also, as I said, we baked in Zenoh inside Unreal. So just a quick example of more or less how we are doing, and that's everything I like of Zenoh, that we can just integrate depending on the technology. We can just integrate in that case in C++, right? So we have on the left side how we imagine we have the one camera model receiving images, then we cast into protobuf, and then we are doing some pre-processing, in that case encoding to a JPEG using this is a library that I'm developing on the side, Cornea, that now I have also the C++ bindings, and in that case we are encoding the raw image from the game viewport, encoding to JPEG and sending over Zenoh in C++. So yeah, that was a bit demo results, etc. And I also wanted to open here kind of a call of what we're doing in the lab. So we are now, I mean, we are open to collaborations. So our initiatives are always towards collecting data sets, is possible collaborative for outdoor applications. Now it's farming, but we are starting also other kind of applications, for example, mining. We are also experimenting with foundational robotics models, which probably soon will start probably around flavor, either fine-tuning or just starting something else. And we are organizing already workshops, hackathons, courseware will come. I didn't mention, but with the Amiga, there is already, this is coming already from FarmNG, but there is already a 4-year challenge that is called the Robotics Farm Challenge. It's mainly based on US, but I'm aware that international participants are also invited to participate, where just teams, initially they were just using the Amiga, but I think now it's more open to different robots. So, and well, we started that at FarmNG, now with Bonsai, this continues. So this means that every year, different universities, so last year we had up to, I think, 100 universities participating. So it's like a good place to get also good use cases, learnings, etc. And of course, yeah, Zenoh is open source. We leverage open source. Part of my team also, well, we develop the Cornea library. In the background, there is also people from OpenCV that is also helping in this direction. And we are always happy to help to contribute to other yeah, open source libraries. So here is also a call for open collaboration. And I think that's it. If there are any questions.
Well, first of all, thank you very much, Edgar. Pretty interesting presentation. And obviously, we were very glad to see, how you expanded the use of Zenoh in your system. That's pretty cool. Yeah. And the demo is pretty impressive.
Very good.
Yeah, I mean that was.
Yeah. It was. I was also impressed that how easy I could integrate, for example, Zenoh inside Unreal. And so basically now it means that we have this system. It's a headless in the end simulator that we have interactivity over Zenoh, and now it's we have hosted in the cloud. The first versions it was local, but definitely I think at some point I would like to try to investigate more because now we use like a proxy always, right? Intermediate applications, but I'm pretty sure that yeah, we could leverage more of the networking for Zenoh, just to operate. I mean, just to interact with the simulator, right?
And on your robot, are you leveraging shared memory for
not yet, but yeah, but this is something that we are really interested in.
Because you know that you could write the shared memory provider straight for the GPU potentially.
Yeah, I mean, actually, yeah, you told me before. This is so okay. This is something that the platform team. So now I'm talking more on the research team. This is what we do for the research.
Yeah.
And the platform team, I'm aware that they are starting now already to look in this direction. Part of thing is we discussed about this some time ago, and I think that very soon the team will start to look into it again.
Yeah. And then, I mean, no, I don't know if everyone is aware how complicated is farming, robotics in farming.
Yeah.
Because the environment changes all the time.
Yes, exactly.
The plants grow differently, actually, in different parts of the world. I mean, even if you need to detect leaves, they are not the same in different parts of the world because it depends on the inclination of the sun. I mean, it's very fascinating. Yeah.
Yeah, and actually it was part of the motivation why originally the Amiga it's modular. So that's because you were going to its farm, and the rows are different size. So that's the first thing you encounter, right? And if you have like a rigid robot, you're done. I mean,
absolutely. Hey, let me bring on Guillaume.
Yeah.
It doesn't do farms, but it does something quite interesting too, which are warehouses, isn't it, Guillaume?
Quite big environment.
Hello, everybody. Can you hear me okay?
Very well,
yes, perfect. So today I shamelessly reuse a presentation we gave at the last ROSCON with Julien.
Okay. Edgar disappeared. Edgar, hold on. I mean, you can come back. I wanted,
Okay.
We wanted to greet you properly. Well, it's
no problem.
Okay. So thank you very much again for your presentation, and keep up with the great work. Ciao. Bye bye.
Thank you.
And very interesting to see what Edgar presented, because it's also using ROS, as I understood. So I'm going to continue on ROS, and we're using most of the things that we presented at the last ROSCON in Singapore with Julien. So I'm going to go relatively fast in the beginning. If you want more details, it's our talk is online. But it's mainly to tell you what we do with Zenoh at Dexory. And what we are planning to do in the future, which is a part that we didn't have the time to discuss that much at the ROSCON, and where I will try to spend a bit more time today.
Okay.
I was hoping to have Matt, who is a VP of software at Dexory, to join, but last minute he had an important critical meeting, so I don't think he's going to join, but I'm going to cover for him.
Okay. So Guillaume, the floor is yours.
Yes.
We are going to disappear for a moment. We'll see you at the end of your presentation. Enjoy.
Great. So let's see if this is working. So for the one, we are a bit far away from ROS, and we don't know what and who Dexory is. We are like a company based in the UK, and we manufacture very big robots that our CEO loves to say it's the tallest in the world. I'm not sure that's true. And it's a big machine, 750 kilos, up to 14 meters, 18 meters very soon. But the interesting bit is that it's using a huge ROS stack with many, many nodes, and with lots of 3D LiDARs to manage. We are using and leveraging a lot the open source robotics community. So we are using ROS2, the latest version, and we are using to power the navigation of our robot, NAV2, that we are very proudly sponsoring since the beginning and still contributing today. But for the topic of the day, and for Zenoh, what's interesting before everything else is the fact that we have lots of nodes, topics, and services on our ROS2 stack, which is definitely a challenge for the middleware. And also, everything is running on the same machine for the ROS stack. And this is what we presented in Singapore. We actually did the migration from RMW C-Clone, yes, to Zenoh this quarter. So we don't have the whole fleet migrated yet, but we are migrating every week a couple of robots. And we've been working for the last 6 months with Etascale to make sure that Zenoh RMW could work properly with the ROS stack. And I'm going to give you a couple of tips and results that we learn along the way. So first, with Zenoh RMW, the number of TCP sockets used grows quadratically with the number of process, which can be a problem if you don't configure well your system. So I'm not going to read all of this. I'm just putting the slide here. There are a couple of Linux system configuration that you can leverage to make sure that everything runs fine, many port configuration. And also for the ROS user, by using composition, you can also decrease a lot the stress on the ROS graph. An example for us was just to migrate our monitoring node to just one component manager, so composition, and we reduce the number of sockets used by 5,000. And also another mechanism that we leverage, which is very important for us, is shared memory. So in ROS RMW, this is you can enable that by using the Zenoh config override with the string that I put there, or using, I believe, like a configuration file. And the first time we enabled it, we had some issues with the shared memory mechanism falling back to TCP communication for big messages, and we had to investigate what were the biggest messages on our stack. So we knew that we had LiDAR message that could be pretty big, something like 10 megabytes, but actually it turned out it was all our maps and occupancy degree structure that were the biggest. And it appeared also that the biggest map that we have on our deployed site is 1.1 kilometer long and up to 200,000 square meter. And that is resulting in a message which is about 100 megabytes. So for this to work with a shared memory in RMW Zenoh, you need to configure the shared memory alloc size according to your biggest message. And if you don't want to have all your nodes to share the same configuration, you can actually do the configuration, the parameterization per node, which is quite important if you don't want to just reserve way too much memory. How it works, I leave it to Julien, and you can watch his explanation on our previous talk, which is online. But for me as a user, I can tell you that it's working well. And it's like much more efficient than when you're on the same machine than using TCP over loopback. So something that we had to do also was to check all the QoS depths configuration on all of our nodes, and in the process we realized that there was a couple of aberrations. A very dramatic example is one of the laser filter scan-to-scan filter chain node, which is configured by default with a queue of 1,000. So with a queue of 1,000, there will be 1,000 times the size of the shared memory allocation that will be reserved in memory, so which is not really optimized. So watch out for that. And on the right is an example of how to configure per node the alloc size, so you don't apply the same configuration everywhere. In terms of performance, we had immediate gain by using shared memory with Zenoh RMW. On the top of this slide, you get you see the traffic that we have on our loopback interface with Cyclone RMW, which is about 500 megabytes a second. And with Zenoh RMW and shared memory enabled, we basically drop the network communication to 0. The way to check that delay, I think it's just a standard CLI network command to check that on a Linux system. And in terms of performance, I still hope to publish in the next couple of months a more granular analysis than what you're seeing there. But we compared the performance as the CPU usage on our robot in a real warehouse scanning scenario. So the robot scanning and navigating and planning and avoiding obstacles for 30 minutes. With Cyclone RMW enabled on the left and with Zenoh on the right with shared memory enabled. And what we observe is that we have about 20% reduction of CPU usage, which is an amazing gain that we got for free with that migration. Very few words, but I'm not going to, again, go into much details. Because of the size of our stack, the bring up and starting all of our nodes together is causing quite some stress for RMW Zenoh. And this is where using shared memory is important because it reduces a lot of stress. And our stack works well and is stable with shared memory. Without shared memory, we still have a bit of bring up challenges, but I believe that Julian mentioned that Zeta scale, you guys may work on improving those kind of issues. But long story short, for us, it's working well, very well with shared memory. And again, we are using the very last version of Kilt and the very last version of the RMW Zenoh CPP. But now the interesting part, if we have RMW Zenoh enabled on our ROS stack, that opens lots of potential new use cases for interacting with the resources that are in the ROS stack. And I'm going to go into details now. One thing that we did with the test canon, which is released open source now, is what we call the Zenoh MCAP writer, which is a piece of software which you can run in a non-ROS environment, and that will be able to dump MCAP ROS bag by subscribing over Zenoh to ROS resources. For us, the use case is a perception application that needs to have access to the low-level stream of 3D LiDAR that is managed by our ROS container, and that needs to analyze this data in a non-ROS environment. You can have many reasons why you don't want to use ROS, specifically if you are doing machine learning or heavy GPU inference, and having this MCAP writer simplify a lot the architecture and the interaction between those two subsystems. And what I call the cherry on the cake, if you want to have a MCAP ROS bag to be written exactly as if it was written in the ROS environment, your MCAP writer needs to have access to the schema and the type information of the topic it's subscribing to. And this is where we have the ROS2 type registry, which is an executable which is running on the ROS side and which is exposing over Zenoh the type definition. So the MCAP writer in the non-ROS context can have access to the ROS definition of the messages. And this is quite powerful and simplify a lot also the management of versioning between the ROS container software and the non-ROS container software. And next and future development that we are considering at the moment is to leverage Zenoh for replacing outside ROS what you have in the ROS bag, which is called the snapshot mode. So to have an in-memory buffer that is being dumped into a MCAP ROS bag based on some trigger generated by an event monitor. Event monitors that could be triggered by the ROS stack or by all the non-ROS applications that we also have in our system. And finally, the future development that we are definitely going to push next quarter, and we have to think on that with Angelo and Julian, is the one that is the most exciting to me, which is to be able to migrate our old architecture, which is using a gRPC server inside a ROS container to expose an API to non-ROS application in order to have an interaction between them. So typically for a non-ROS application to trigger a navigation action. So currently with our gRPC server and we have many layers of API to expose a sample ROS action and the feedback and the results. What we envision is to have a Zenoh action wrapper living outside the ROS environment and being able to interact natively with a ROS action, meaning that our ROS action will become our external API for non-ROS application. And that's very exciting because it will simplify a lot of architecture, and two, will probably squeeze a lot of performance out of it because there will be less layer of copy, and three, it's much clearer in terms for development and much faster iteration. So if we were to add a field on a ROS2 action, it will be immediately accessible on the API to non-ROS application. Similarly, and it's not written on this slide, but we are hoping to make it easy for non-ROS application to access position and generalized TF information. And it's probably something that we need to look soon at, but I've seen that there is a new RCLGS 2.0 library that's been published. And for me, I think it's one of the best examples out there of wrapper of TF or wrapper of ROS action outside the ROS ecosystem. So what we'd love to get is to have a similar architecture, not necessarily architecture, but similar advantage that you have when you're using ROS, libjs, and the ROS bridge, but with Zenoh and without having a bridge. I don't know if that's clear, but we can definitely discuss that later. And yeah, that's it. I would have loved to have Matt intervening today, but it will be for next time. And I hope that gives you a glimpse of where we are heading. And the big message for me is also for everybody, RMW Zenoh in the last version of ROS, it is working, it is scalable, and we are using it in production. So now we can focus on what's next.
Many thanks to you also, Guillaume, because you with us you put a lot of effort to debug all the preliminary version of RMW Zenoh, and thanks again for all your help. And I think now all the ROS community can benefit from your experiments.
Yeah, thank you. And that was only possible because you guys were extremely reactive and supporting us a lot. So now today we are in a happy place, and we can think about the new use cases.
Yeah, getting back about your TS, TypeScript, JavaScript. Yeah, I already jumped to that. So there are interesting things we can do because we already have TypeScript support in Zenoh, right? But now we have the no-std version of Zenoh that can be compiled as WASM and told native Zenoh will be more efficient in terms of runtime performance than what we have today, right? And we will support the TypeScript API, TypeScript JavaScript on top of that. So we could do precisely the same if you need to access action from a web browser. It will be a very thin layer on top, so that will be super cool.
And that would be amazing. Yeah, it would be amazing. And the key will be like the usability of exposing the action mechanism, a bit like what ROS libjs is doing at the moment.
Yeah. Okay. So before you drop, let me bring on our next guest, which is Frederick from Sweden. Hey, hello, Frederick.
Hello, guys.
So, Guillaume, terrific presentation as always. Thank you very much. And yeah, let's keep up with the great work. Thank you. Ciao.
See you soon.
Bye.
Ciao.
Okay, so Frederick.
Yes.
So again, thank you very much for joining the Zoom 2025. We look very much forward to your presentation. So I'll bring up your slides, which should be seeable by the attendees. And you are going to talk about maritime robotics, isn't it?
Well, maritime research in a broader sense. We're dealing a little bit with robotics, but that's not all of it. Let's say that.
Okay.
So it's a bit of a different scope than what the previous speakers have been dealing with.
Okay, nice. Sounds very good. That's good. So at least we'll have a little bit more variety. So the floor is yours.
Thank you.
Right.
Thank you. My name is Fredrik Olsson. I'm a research engineer at the RISE Research Institute of Sweden, situated in Gothenburg, and dealing with maritime research, typically digitalization within maritime. And just to give you a short, brief overview, RISE is a state-owned research institute in Sweden. We have over 3,000 employees. The most interesting part here is probably that we're operating over 130 test beds and demonstration environments for demonstrating research that's been done and for testing and verifying new products. Specifically, one of those test beds is what's called the SSPA Maritime Center, and it's been around since the 1940s. It's what's called a towing tank facility where you have large-scale water basins, essentially, for testing model scales, ship model scales, or ship scale models to try out their hydrodynamic properties, ensure that they behave as expected in waves, that the hull resistance is as expected, and so on and so forth. So that's one of the core things that we're doing at RISE, one of the test beds. Me and some colleagues of mine, we're also more into research regarding digitalization in maritime, in the maritime industry. And for us, a typical day can look like this. So this is very much prototyping in a different sense than what the other previous speakers have been talking about. In this case, we are investigating how different types of sensors. On the left here, we have a typical maritime radar. On the right, we have an OS2 LiDAR together with a stereo camera. And we're investigating how these can be used how these can be used to find people in the water. So you see right off the cliff here, we have someone in the water showing up, and we also have a smaller boat out there that we can compare these and how they are seen and how they can be perceived by the different systems, and how these can be later on then provided to a user or in a user interface. And I think this picture kind of brings it all together, what we're doing. It's very much prototyping. You see all the boxes at the bottom. We're doing this for a couple of hours perhaps, and then it's up, and we have a couple of days later, we have another setup that we need to connect, and we need to have our software stack and our hardware stack working in another array, so to say. Another example of this is from a project that was finished a year back approximately. It's called the Reeds project, which one of the outcomes of that project was a gathering of a data set similar to the Kitty data set for in the automotive industry. So essentially gathering a lot of perception data into a data set. This project did it in a maritime setting, so that the data set is now, you can use it for both training and evaluating different types of algorithms that uses perception data. And the stack on board is, the sensor stack on board is, this little boat was actually quite impressive. It generated a lot of data. I think it was a single run of an hour generated some 30 terabytes of data or something like that. So it's an impressive amount of data generated. And I should say that at this point, we didn't use Zenoh for the gathering of the data, but the Zenoh was used as part of the remote control setup of this platform, and for observing it and for controlling it from a distance. We're also partly into robotics, you could say. We have on the left here, it's a small unmanned vessel model that you can't really see it on the picture here, but it's a foiling vessel, meaning that it's actually, once you reach a certain speed, it will lift out of the water, and it will ride on one of these foiling wings that's still in the water. So it's a remotely controlled model in that sense. And then we're using, as you can see, we have quite some hardware and software on board, and we're using Zenoh typically for monitoring and looking for monitoring and having the possibility of probing and verifying the system that's on board. And I'll get back to that. On the right, we have one of the smallest things that we're dealing a bit with. You can see my colleague's dog, who's wondering what the heck has is using his pool. This is a very small scale model that we have. It's something that can be used for autonomous research. So what we can do with this is actually you have the possibility of trying out different algorithms for autonomous steering on this boat, and then we have a monitoring stack on top of it that monitors what the autonomous algorithms are actually doing, so that we can then verify if this is doing what we expect it to do or not doing what we expect it to do. And this is quite similar to what a lot of the product development companies do. I think the main difference with us and what we're doing is that we are typically not evaluating our own software stack. We are using a system that's based on Zenoh, and then we are evaluating, we're testing, we're probing a system that we don't really know much about. We have control algorithms, and we have autonomous steering algorithms that we want to evaluate and see if they do what we expect them to do, and we have some ways of connecting to them, and they can provide us with data in certain means, but it's not our system. And when we started with all this a couple of years back, our main target with this was to develop some kind of open research platform for maritime digitalization, and that was one part of it, is this to evaluate control algorithms and autonomous systems, decision support systems, and our core goal with this was really we see that the maritime industry is really kind of lagging behind in terms of digitalization when you compare to the automotive industry, when you compare to the avionic industry, and so on and so forth. So our thinking with this was that, well, we need to be able to provide this kind of platform for reducing the threshold for starting with these kind of innovations in the maritime industry. We wanted to simplify the setup for doing testing and verification of these kind of systems, and then also guide our partners and clients in both in the technology stack, but definitely also within the requirements with regards to standards and how to verify that stuff works as expected. So this is really the initial idea that we set out with a couple of years back, and the struggle that we've been through, mainly due to the fact that it's not our system that we are wanting to monitor and evaluate. That means that we need to be very flexible in what we can do and what we can connect to and how we approach this. And well, this is supposed to symbolize a snapshot of my and my colleagues' brains over the last, not the last 2 years perhaps, but the previous 2 years before that, when we tried out a lot of different protocols, a lot of different data formats, a lot of different messaging stacks, and so on and so forth, finding out what can we use and what can we not use. And what we learned along the way, and what I've tried to condense into this slide is that really that for us, if we're being a bit crude here, there are two parts that really matters. It's the connectivity, and that is really how data moves in and across systems, and the semantics, so what the data actually means. And for us, with regards to connectivity, we have geographically distributed nodes. I mean, we can have several vessels that are out somewhere on the ocean. We have a shore center where we want to monitor what's happening. We have simulated environments that we want to connect. meaning that we don't have a single network that we can utilize for it. It needs to be geographically distributed nodes. Having stuff out on the ocean also means that we have intermittent connections. It's typically 4G connections that drops out every now and then. Because of that, we need to have the possibility of really in detail decide on what data that should stay on the boat, on the vessel, and what should be allowed to flow into other parts of the network. Obviously, persistence of data, how to deal with that, and where should we persist data in the system in order to maximize performance. We need to be able to choose the topology, and obviously we need to have some secure lines of communication since we're dealing with potentially risky data in that sense, that we're dealing with navigational data and so on with vessels that are active. Semantics, data format, metadata / information, what the data actually means. And then obviously context. We need to know, in order to be able to decode what this data is supposed to give us for information, we need to know the context that it's set in. And on top of that, we have a need for observability of not only the system that we're monitoring, but our system. Does it work as we expect? What's happening with the different nodes that we have deployed and so on? And then obviously, since we are dealing with other system primarily, our system is typically deployed in order to monitor another system or connect with another system. A core concern for us is interoperability. And Zenoh has really solved much of this part for us. And for that, we're really grateful. It works really well. We have on top of Zenoh, we built something that we call Kilson, which is really all about the semantics, and it's tailored for the maritime context that we're working in. For the observability and interoperability part, we have two other smaller pieces of software that's called, it's a Zenoh CLI, and it's called Porla, which are two smaller software stacks that we use really for fast prototyping and for probing our environment, and we'll talk a bit more about those things. I'll give you some short intro to these. One core thing is that one thing that we're still struggling with, and one thing that I could imagine would be a nice addition to Zenoh 2.0 would be a better and more efficient observability of the Zenoh network and the nodes that are in it. That would be really nice. All right, so Kilson, semantics. So you guys all do it. I guess it's essentially it decides. It has opinions about the key format. It has opinions about the data format, and so on and so forth. And we distribute these as SDKs for Python and JavaScript, so it's easy for whoever wants to use it to just pop it into their environment and decode and encode messages on the fly. And the design principle that we have decided to go with is that we have a payload that's described by a schema, and that essentially tells us, it tells your computer, it tells the machine how to interpret the data. On top of that, we need to know something about, we need to be informed about what the data means in terms of what does the data actually mean? And then we have decided to, inside our key expression structure, we encode as one part is something that we call a subject, and that describes how we as human beings should interpret the information. And then the whole of the key expression gives us the context that we need in order to put this into, perhaps the subject says that this is the rudder angle. Well, okay, so what context? I need a context. Which vessel is it? Which rudder? So on and so forth. That's put in the key expression. Moving on to what we call PORLA, and that's a short for pipeline-oriented real-time logging system. And this is something that we actually started using prior to using Zenoh, and it's a really simple thing. It's built on top of Unix pipes, UDP multicast as a transport protocol, and utilizing Docker containers for composability. And then we use Docker Compose files for the declaration documentation of these pipeline setups that we use this for. And we found that it's really good for prototyping at the edge, which we essentially do a lot. So a mental model of this is something like this. You have sources of data coming in. You can do different things with it. You can timestamp it. You can transform the data. You can record it, or you can sync it to some other connector somewhere. And I mean, this is very generic. This could very much be any kind of Zenoh stack, for example. The difference here is that it's all defined by a Docker Compose file. So at the top here, we have a source of data that is coming in through a UDP socket. We timestamp it. We put it on one of our buses, as bus number 1. Then we can, in any of the other containers that we're deploying as part of this stack, we can subscribe to this bus, and we can be base64 encoded, for example. We can output it to another UDP socket, or we can record it, or really anything that we have the built-in tools for. And this is the really good thing with this, is that it's quick and easy to work with when you're sitting somewhere and just need something that works. But it's also self-documenting, since the declaration of this is all the documentation that you really need. Together with our, I call it the poking device. So essentially the thing that you try to poke your Zenoh environment with. And I know that since we started with this, there is a lot of different options that's shown up. There are now, I think there are command line interfaces for Zenoh in Rust, and it's this new shell that the Zenoh guys presented earlier today. There's also one in JavaScript, I think, so on and so forth. And really, what this is in Python, and one of the reasons that we developed, or some of the reasons that we developed it for, is that we needed something that had that we could use together with our semantics. And then we decided to make it generic, so it has support for codecs as plugins, so you can supply encoders and decoders that encode or decode messages on the fly. It supports standard in and standard out, but natively, meaning that the main thing with that is really that we can use it together with our previous tool, PORLA, as one of these Unix pipelines. So we can pipe data from one source and directly stream it onto a Zenoh pipeline and encoding it to the format that we need on the fly, which is quite handy. And it has some simple built-in network visualization. So this is an example of how it can work. We can start a subscriber in one, and we specify that the decoder is something that's exported from the Keelson package. And here we have on the bottom, we have a publisher. We specify that on each line, we have the first is a key. That's the key that we will publish on. And we have the value, and it will publish. And it encodes it using another one of the encoder that's exposed from Zenoh. Yeah. And then this is an example of the network visualization. So it's just a simple thing just for us to kind of get how does it actually look right now? Does it look like we expect it to do? It's a small step in terms of observability, and I know that the Zenoh guys have a lot better tools, but I'm not sure if all of them are open for access to anyone. And then just a couple of weeks back, we decided that we were kind of bored and we didn't really have time to write microservices for all of the prototyping that we wanted to do. And since Zenoh guys now have deployed or released the TypeScript interface for Zenoh. I decided to give it a go to see how I could get it to work inside the Node-RED to get really fast-paced prototyping, and it worked out really good. So there is a Node-RED integration with Zenoh that's totally workable, and you can do both publish and subscribe, and you can do query and queryable in any way you really like. And of course, for us, we also have our nodes for our semantics, the Keelson package that we can encode and decode messages once they arrive into Node-RED. And as an example for how we use this or intend to use this is this. On board a vessel, this is a simplified image, but on board a vessel, you typically have at least one GNSS receiver, a GPS receiver, and you have a navigation system, an ECDIS navigation system. And you can imagine on more modern vessels, you have also a software stack which includes decision support algorithms or autonomous algorithms and so on. And what we can do now with really simple tooling is that we can act as a middleman in between these. We can use the tools that we have. We can stream it onto an onshore if we want or need. We can stream it onto an onshore shore center into Node-RED, and we can play with different kind of failure injection logics. So for example, GPS spoofing, and then send it back on board and see and evaluate how does the crew react to this. That's one use case. And just as now we'll skip on to a totally different subject for a while, just to showcase what Zenoh also can be used for, which is very far away from robotics in that sense. And that's we also work a lot with sailing ships, sailing cargo ships, and these are typically as of now, there are not many of them actually sailing out in the real world, meaning that there is a lot of digital models so far of these kind of ships, and there is a lot of simulations going on. There's a lot of simulations done on these types of vessels in different configurations for different purposes. And one of the things that's being simulated, and one of the questions that are being asked is, well, how does the different control systems on board these vessels interact once you're out on open sea in different scenarios? And in order to answer that kind of question, you really you need good simulation models for not only the ship, the hydrodynamics, the aerodynamics of the wings, but also for the control systems and the control system logics and algorithms. And in order to kind of compose that kind of simulation model, which has good models of all of those parts, we figured that the best way and the easiest way was actually to make sure that we could integrate the manufacturer's own simulation models rather than us re-implementing things or implementing generic things. And in a project that's still ongoing, we have implemented a tool that's called Liaison, which is it's enabling geo-distributed co-simulations, meaning that, and it's based on a standard that's called the functional mockup interface, which is an open standard for exchanging dynamic simulation models. And what it really does is that we can, as an example here, then using Paris and Gothenburg as an example, is that we can have a simulation engine, the main orchestrator of the simulation running in Paris, but we can have one or several of the simulation models that are part of the simulation deployed in Gothenburg. And that means that we can set up a co-simulation with different manufacturers and different equipment providers without having to ask them to reveal their intellectual property in terms of code or simulation models or descriptions. We can just ask them to just provide this interface for us, and we'll simulate it happily across the internet. And that's it for me. That's the short story of all the different things that we do at Rice Maritime for digital plumbing, you could say. That's the name I used for this.
Well,
Very
thank you.
nice.
Yeah, very nice. Thank you very much, Frederick, because it was very interesting, multifaceted, because
Yeah.
indeed there were quite a few use cases that are very interesting. Your pull request was just merged. Okay. No, that's great, right?
No worries.
Yeah,
No
no,
worries.
that's good.
Yeah.
Yeah. So I did.
No, I mean, and I think is what it really shows is that as a research institute, we really do have a lot of different things, and our main headache is really the flexibility. How can we support all of these things without having to have 5 different software stacks? And that's been the main headache, and Zenoh has really helped us solving part of it for sure.
Yeah. So something that was interesting for me, I didn't see yet any use in constrained environment like microcontrollers. Is that something you are going to look at next, or?
Well, maybe, but it really depends a little bit, because it's typically looking at ships. They are very big.
Mm-hmm.
You don't really have the need for small microcontrollers in that sense. But on the other hand, we're also more and more dealing with smaller autonomous unmanned surface vehicles or surface vessels, and within that scope, I definitely think we'll be venturing into more of microcontroller perspective of Zenoh as well.
Okay, that will be quite good to see. And by the way, if you come to Paris, you're always welcome to visit us. And next time I come to Gothenburg, Gothenburg was I know it quite well, because I lived in Scandinavia, not in Sweden, for some time. So I'll give you a shout. Okay.
Do that. Perfect.
Okay. So let me bring up the next speaker before we greet you, which is Alejandro. Hello, Alejandro. How are you?
Hello. Fine. How are you guys?
Great. Okay, Frederick, it was
Thank
a
you.
pleasure to have you on our Zoom. Great presentation. Keep up with the great work. Thank you.
Thank you. Bye.
Bye. Okay, so Alejandro, are you ready?
Yes.
Great. So let me bring your screen up, and the floor is yours.
Okay, thank you. So, hello everyone. Yeah, so I'm Alejandro, and a year ago, more or less, we introduced RNW Zenoh for the first time as alternative middleware that you can use with ROS2, which is not TDS based. And today we'll explain some of the progress that we have done during the last year. So, coming from the new hope of an alternative middleware to a Taiwan. So let's go with okay, here. Yeah, so my name is Alejandro Cordero. I am one of the founders of Home Robotics, and I am, in this company, we are helping robotic companies to use ROS, to use Gazebo or simulators and set up things on CI. And I have been engaged with the ROS community, Gazebo community for a long time, probably something around 9 to 10 years. I am already part of 3 PMCs, ROS and Gazebo. So PMC are the weekly meetings that we have that we make decisions. So in ROS and Gazebo I can vote, but in ROS2 Control I am only a member, but I can merge PRs. And I'm also the ROS2 representative for the TGC. The TGC is a high-level meeting that we have every month, more or less, and we are deciding which is the path of the ROS2 Gazebo and all of these things. My GitHub handle is Cordes, so you probably know me if you are in this world, because I am maintaining almost every ROS2 package right now in the ROS core, and as well as RNW, which is right now one of those. So again, a year ago, we announced that RNW was feature complete. So that was the first time that we shared that we have been doing. And we introduced a feature complete RNW that, it was a minimal version of an alternative middleware already. And this was able to do PubSub apps, services, actions, and some basic introspection through CLI. But we made at that time also several promises, and one of which was to convert or to get RNW Zenoh to Tier 1 status by Kilted, which is the recent ROS distribution, and together with some fixing some bugs and getting it more stable for everyone. If you ask me for today, so we are announcing that RNW Zenoh is a Tier 1 platform or middleware on ROS 2. So what that means if you are a Tier 1 platform in ROS? So Tier 1 is just a special status that we assign to certain packages in the ROS 2 ecosystem. So in short, it means that RNW is now a ROS 2 core package, which is inside the Rep 2005. And with that, it comes with some guarantees over quality, stability, and support. We have to essentially was firstly to get all the core tests to pass. There are several thousand of tests in the ROS 2 ecosystem that every new middleware has to pass against, and we made it. Then we have security. One of the main design decisions between ROS 1 and ROS 2 was to provide security by means of authentication, access control, and encryption out of the box, and this is also included right now. And we also need to support all the Tier 1 operating systems, which are defined in the Rep 2000. We now are shipping binaries on Ubuntu, whether it's R64 or x86 platforms, together with binaries on Windows. And we also support compilation on Mac as well as Debian. Quality is top of the cell. So we also adhere this to the Rep 2004 that, said you have to complete some quality guidelines. And again, all the core packages need to, pass through this RNW to get it at Tier 1. And it will stay in that way for a long time, we hope. Me as a maintainer, and also Julien, Jaru, and Jujuan, we are committed to maintain the RNW Zenoh with certain level of stability. I would like to remember that only Kilted are rolling are Tier 1. If we are talking about Jassy and Humble, then these are only community supported. But I would say that code base are very similar. So there are some guarantees, but not all of them. What else? So talking about this test that we need to pass. So we have a nightly job that is running every night, where essentially we are running RNW Zenoh and if it were the default middleware in ROS, again, every package in the ROS core in our build farm. And these are, more than 40K tests that we are running every night. And if something is failing or something is not properly done, we will be notified the maintainers, and given the quality declaration that this package has, which I think is 1 or 2, we should fix it and provide a fix for that. But we have done more than that, not only convert this into Tier 1, we are also adding more features. The first one that I want to talk about is the shared memory. So RNW Zenoh supports shared memory in a transparent way, meaning that any RCL API, any package with any type can use it, including variables length type definition. The data will be serialized directly in a shared memory buffer, and it can be accessible to any subscriber. And if a router needs to send it over the network, over the Wi-Fi, it will read this chunk of memory, and it will, save it over TCP. There is no daemon used by Zenoh. So to manage the shared memory, each process will manage its own shared memory segment. Zenoh also take care about the garbage collection, the fragmentation, and cleanups. And if we are talking about also containers, many people are using Zenoh inside containers. It can be used, so you can use container with ICP host, or even declare a common /test/shm volume between all containers for shared memory exchange, and you can, share memory between all of them. All right, what else? So QoS override, so what I mean? So it means that by configuration, you can change some quality of service of your application directly on your node. So you can change the behavior which regard what you have developed in your node. So you can change it directly by configuration or even on the fly, configuring just the router. It means that, for instance, if you may have a reliable topic inside your robot, but then you want to route this over the Wi-Fi, you can switch this topic to best effort, for example, in order to avoid the slowdown your router, your publisher in your robot. If we talk about security, so we are supporting the ROS2 security command line tools that you can generate SSL certificates, and you can also get your private keys for your application. And it was myself who write this package. It was the Zenoh security tools that it will allow you to generate some of the policies and configuration files for, use this with mutual authentication or to set the policies for access control that allow you to set which topics do you want to send to or are accessible from another node. But we have been also shipping some small improvements. So in recent releases of Zenoh, and for instance, we have the transport compression that you can configure the router for compression on the fly of the messages, and it will give you a good result, I would say. Then we have the low pass filter, will allow you to set the router to drop very big messages over the network to avoid congestions on your network. Also, we have the congestion control. It's another feature that allows you to decrease the congestion of your network, and you can make sure that at least one message passes over the network from time to time. And then we made a lot of improvement with regard latency, jitter, and throughput during the last year. So right now it's time to measure what we have done. I know it's tricky when you are measuring things against other competitors and so on. So I will highly recommend you to test this with your own platforms, with your own software, with your own hardware, because it will give you a much better intuition about if RNW Zenoh will provide you better results. But we have here some results that we have done, which are matching with some other results that some people have shared in the community. So I will explain to you which are the benefits of using Zenoh. We have the Apex AI benchmark test, which is measuring the mean latency with multi-process shared memory up to 10 Hertz. You can see that Zenoh for small messages is not performing as good as the other RNWs, but for big messages, it's performing much better. Big messages means cameras, LiDARs, point clouds, and so on. If we run the iRobot benchmark test, and we are measuring the publisher latency with multiprocessor memory up to 200 Hertz, we can see that the latency is for big messages is less than 200 microseconds, and for small messages is very small. So I would say that it's pretty decent. Then if we are doing the end-to-end, which is sending a message and receiving the message again, measuring also the latency with multiprocessor memory and up to 200 Hertz, we can see that for big messages, it's up to 600 microseconds, and for small messages, 200 microseconds. Then we have an in-depth analysis with our colleague Skyler Medeiros, which is one of the main contributors these days in the ROS core. She has done some benchmark in September 2025 this year. These tests are showing that Cyclone is not using shared memory, but the other ones are using shared memory. And we can see for small messages, again, we are pretty close to the RNWs, but for me, for big messages, the performance of RNW, I would say that is much better. And in terms of CPU load, you can see here that almost every RNW is performing very similar. RNW Zenoh is more or less in the middle. So I would say that is expected, right? These results. But I mean, we can do more with all of this. So with Zenoh, so the answer is yes, because Zenoh is kind of redefining the way that you can architect your own robot solution. And I would like to give you like a flavor of what it looks like. So when you are, a common use case when you are building your robot is that you may have one main computer that is running your perception, your control, your brain stack. These boards often communicate with low-level microcontroller boards. And with RNW, you can have, like ROS node running on RNW Zenoh on the main computer, and together with RNW router. But you can also have some nodes powered by Pico ROS on a microcontroller. So Pico ROS is a fantastic contribution by Ubiquiti Robotics, and it's a lightweight wrapper around Zenoh Pico, and it will allow you to write cool things like this, which is, you can deploy code on your ESP32 or other microcontroller, where you can set up a ROS node, create a publisher, publish your odometry message, or you maybe can subscribe to a robot command reference and then move your wheels. And you can have it publish this topic and add, to the main computer side, so you can just subscribe to yet another ROS message. And this is, like really great. And we have been using this extensively for application where we have been, building robot, talking with motors, talking with IMUs, odometry sensor, etc. Then we can fine-tune a little bit the performance. So one of the challenges that we have seen so far, especially at lunchtime and startup time, is that if you need to start a lot of nodes in your system, like meaning that you have point clouds, you have LiDAR scans, and maybe you have some other nodes like localization, doing localization or planning stack, but aren't getting initialized because there are some congestion on the network. We can fine-tune this. And this happens a lot with the map topic or maybe occupancy grips. And with RNW Zenoh, you can fine-tune the transport performance on per topic basis. So you can set priority and congestion control settings for topic, like the MAC, for example, and you can guarantee that it will deliver when the ROS start. So right now that we have fine-tuned our performance on a single robot in the main computer, the obvious next use case is that, okay, how I can make these things talk together, each one with another. So with RNW, that's very simple. It's just connecting the router on your robot to other routers on your cloud systems. So you could have your fleet managers, your fleet management stacks or your dashboard running on your cloud system and simply talking to your robot on the factory floor. So what else? Is there something else that we can do to improve Zenoh? Of course, we can do it. So we have a huge push, right, from barely working to Tier 1 middleware over the past year. And there are a lot of exciting, like things that we can do and we want to work on, leading to the next release, which is going to be Lyrical Luth. Lyrical Luth will be released around May, more or less, and it will be a long-term support ROS distribution. And these are the topics that we want to improve. So we would like to make the key expression a lot of simpler, and that's why for low like microcontrollers and so on, memory is very important, and right now the key expression is very big, so we would like to do some improvement there. There's also a very popular feature from user that where they want to be able to dynamically apply namespaces to topic going out of the robot. So maybe you have a robot and you are subscribing to just the velocity command, but the router exposes this to the fleet management system, and it will automatically assign like a robot 1/common velocity key expression. So that will be like a very cool feature to have. Then we are improving the ability to manage and prioritize the congestion control. Also being able to start the router automatically because right now we have to start a different process. We can rely on plugins upstream, so that will be another focus. And something really important, I would say, I think that Julien mentioned this before, when you were talking about how to improve or when you want to see this in the next RNW and 2.0. So something important in the graph cache. So we are implementing this logic to be able to keep track of all the nodes within our system. And this is done through a graph cache. And if all of our nodes, we are running this. So there is an opportunity here for these nodes which are running in the same computer to use the same graph cache, maybe using shared memory of other tool. So we will require some help from the community because we are a small team, and that's something that requires some efforts and designing and so on. So if you are interested in doing this kind of thing, please come talk to us, because everything is happening on GitHub, everything is public. So we would love to have you to contribute to the project. And finally, I also want to ask you for help in the case that you are benchmarking RNW Zenoh against your robot or your application. So we would like to see and to understand which are the pain points that you are having, and if we can improve somehow, the workflow that you have for your application or your robot. And finally, I would like to thank you everyone who has helped during the last years, not only this last year, to make this project possible. And I don't know if there is time for questions, but happy to take any questions.
Okay, so well, first of all, thank you very much, Alejandro, for your presentation. And question typically are in the chat. So there are no questions right now, but look what happened. You say tier 1 3 times, and I end up with this t-shirt. Beautiful t-shirt.
Yeah.
I couldn't resist, right? It was in my office. I said, okay, I'm going to put again the sweater because I feel cold. We are in Paris.
Yeah, I feel a little bit cold. I mean, it was,
exactly
good to have it.
Yeah. So we'll keep an eye on the chat. You keep an eye on the chat. Any question on our side?
No, I think the plan is clear for the next improvement. And again, Alejandro, thank you very much for all your support in making RMW Zenoh, testing it, and for all the ROS ecosystem in general, right? Because you're doing a tremendous job for the whole ROS 2 ecosystem.
Yeah. And again, I mean, among the list of new features that you mentioned, of course, shared memory will be great, but quick multi-stream will be super important, because we'll be able to do priority at no additional resource cost or configuration complexity, right? Which will be cool. A single endpoint, yeah. So I think that is my favorite.
Yeah, and something that people don't think about it is that sometimes we are not only need coding, like helping in coding. If people are testing this in their own real systems, we are really happy, to get their feedback and to improve the workflow or the issues that they are having.
Yeah.
Because at the end we are testing some specific use cases in the build farm, which are very reduced, but then real cases, real scenarios are the ones that break the stack. So really happy to get feedback and to see how people are using it, because there are some use cases that we are not aware and we can also improve it.
Yeah. So let me bring Léonard online. So let's welcome Léonard.
Hello.
Bonsoir Léonard, ça va?
Ça va.
Okay, so Alejandro, thanks again for your presentation. See you around. Ciao.
Thank you, guys. See you.
Ciao.
Bye.
Okay, and we slightly move to a different topic, because we are going to discuss security, isn't it?
Yes.
No. This is not what I'm looking for. Here it is. Okay. We're going to discuss security. So let me bring up your screen. Yeah, your screen is there. And if you're ready to go, the floor is yours.
Okay. So thank you very much, Zscaler, for inviting us for this Zenoh Day user meeting. And thank you for all the speakers for the interesting talks. So I'm with the company Linear. And today I'm going to discuss what we did regarding broadcast encryption on top of Zenoh for secure IoT communications. So to start, I'm going to present a bit who we are as a company. So we are Linear, and we are building cybersecurity for next-gen trusted cloud and AI. We are made up of experts in cryptography from École Normale Supérieure and SecOps engineer from ANSI. So myself, I am a PhD in cryptography from ENS. And what we do is two things. So first, we build off-the-shelf security solutions, so products for companies. And also we do research and development projects for next-gen security. And sorry, what I'm going to talk to you today is going to be the latter. So this is going to be an R&D project that I worked on as a cryptography research engineer. So the goal is to secure communications using end-to-end encryption. End-to-end encryption consists of encrypting data before it leaves a user's device, which is going to be a sender in that case. And we're going to decrypt that data after it enters the receiver's device. So you can think about WhatsApp and Signal for examples of such things. The project, the R&D project I'm going to present today deals with multi-device secure communication. This is a project that we did for the Thales company. So we are we're interested in communication security, where many devices are going to discuss with one another. They're going to have different hardware, software stacks. And so dynamic participation of devices means devices can enter the network, leave the network. We need to be able to handle that. I'm going to give you a fictive example of how this could be applied. So this is not really what we did for Thales, but it works well as an approximation. So we have cars on the road that are going pretty fast, and we'd like to have these cars be autonomous. So they're going to discuss with one another to know their relative positions, their speeds, to be able to smoothly go with traffic. We could even imagine with that to have even more cars than we have on the road today, driving at high speed, maybe even higher speeds than what we have today, very close to one another. But this is very critical as a system, because any kind of mismatch between or misunderstandings between the cars, and we could have a collision at high speed, and this would be a disaster. So we have lots of devices, a lot of cars, lots of sensors, connected road signs, and we need to secure each and every one of these communications. So for security, we need confidentiality. So data that must stay private stays private. Authenticity, you know that when the car yellow speaks with the car, the white car in front of it, it really comes from this yellow car. And integrity. That means that messages are not modified after they leave a user. And the solution for all of that is going to be cryptography. So we have cryptography today, but I'm going to talk about the limits to existing tech. So the traditional way that you would do this, it would be to have so cars on the road and some central authority, maybe the factory that built this car, that is going to distribute keys to these cars. And then we can have host-to-host encryption, but it's a static configuration. So that means that if we add another user to this network, it's going to be a problem to be able to have them interact with the others. And even so, there are going to be a lot of interactions, right? Because every car must interact with every other car. So this can be computation heavy and bandwidth heavy. We need to reduce that. And in addition, classical public key cryptography is not quantum resistant, which is going to be another problem to future-proof such project. So I'm going to go into detail into each of these points one by one to give the broad strokes of what we did, the solutions that we have, and plans for the future. So first, let's go back to basics, and I'm going to give some reminders about symmetric encryption. So in symmetric encryption, Alice and Bob need to discuss over an unsecure channel. So let's say Alice wants to send a message M to Bob, and they both share the same symmetric key K. Alice will use this key to encrypt the message, then she'll send it to Bob, and Bob can use the same key to decrypt the message. So far, so good. The problem is going to be, how do we distribute this key? In the past, you'd have diplomats going with a secure luggage that handle the keys, but we can't do that today because it's clearly not fast. So we're going to use public key encryption for that. In public key encryption, Bob has a public key that we can see more or less as a mailbox. And anyone can send a message to Bob by encrypting it using the public key, which is like posting mail in Bob's mailbox. But Bob is the only one that has a secret key that can decrypt this message. So now, without sharing the same key, it's possible to send a message to Bob by only knowing the public key. The thing is, in practice, public key cryptography is very computation heavy, way more than what we have with symmetric encryption. So we use what we call hybrid encryption, where we are going to mix symmetric and public key cryptography together. So if Alice wants to send a message to Bob, she'll use a random symmetric key. She'll encrypt the message she needs to send to Bob, and then she's going to encapsulate, so encrypt, and we call that encapsulate the symmetric key with Bob's public key, and she'll give this message to Bob. So we call this a key encapsulation mechanism, or KEM for short. And this has been in use for decades, but there are still limits to standard cryptography. For example, if this taxi wanted to send a message to 2 people among 4, so in the bottom left, we want to send a message to those that have a thumbs up. Well, you'd need to encrypt, even if you need to send the same key to everyone, you'd need to encrypt it n times for n people. So you do CT1 for the first person and CT2 for the second. A solution to reduce the overhead that this is going to incur is to use something that's called broadcast encryption. Broadcast encryption was introduced in the 1990s. And so here, broadcast is a bit of a misnomer. In network computer science, it's what we would call multicast, where, so here the taxi is going to multicast to everybody a single ciphertext, CT, that is going to be shorter in size than the sum of the sizes of the ciphertext that we saw in the previous slides. So now with this ciphertext, there is a target set, those with the thumbs up, right? And they're going to be able to decrypt. And the rest of the members of the system are not targeted, so they won't be able to decrypt it. So this is going to this project that we are building. And just to touch upon quantum resistant cryptography, so quantum computers are getting better and better, and it's been proven since the 90s that if we have a working quantum computer, then all of classical public key cryptography gets broken. It's using Shor's algorithm, but new quantum resistant crypto is being developed, becoming more mature, and getting standardized. And so right now, there is an algorithm, a system called Kyber, that was standardized by the NIST, which is the American National Institute of Standards in Technology, under the name MLChem, for Module Lattice Key Encapsulation Mechanism. So, with all of this that we just saw, we're getting to our proposal, which is post-quantum broadcast encryption. So, recently, a paper by Joel Alwen et al., so the link is at the bottom left here, is about multi-recipient chems. And the idea is to modify this Kyber crypto system into M-Kyber, where one ciphertext is going to target multiple recipients. So I won't go too much into the technical details, but the gist of it is that a Kyber ciphertext looks like this. You have this big orange part and a green part. And the orange part, with some theoretical mathematical work, it's possible to make it really not depend on the public key. And when you need to send n-Kyber ciphertexts, you can, so using these techniques, you can factorize this orange part. And so you can send a message to n recipients, but you only have one orange part and n green parts. And to give you some orders of magnitude, so one Kyber ciphertext in the standard security configuration is 768 bytes. So if you want to send a message to 100 parties, it would be more than 75 kilobytes. But if you use M-Kyber to send one message to 100 parties, it's only a touch over 5 kilobytes. So this is a pretty drastic reduction. So all of that was for the theory of our system. So really, it's a research and development project, but we got with a prototyping. Sorry. So now we can get back to our example use case, right, with connected cars on the road. Well, we need to have, for example, an emergency vehicle be able to broadcast get out of the way message, but this needs to be authenticated so that only, for example, an ambulance could be able to send this message. Also, the police could be able to discuss police work over the network, but it needs to be encrypted so that civilians do not have access to this communication. And we would also be able to have, so for example, traffic lights could broadcast the state that they're in. So a traffic light could say, I'm red or I'm green, but you'd need authenticity for this message, because if the wrong message gets sent, it could cause an accident. And also you could have role-based access control for that. So for example, a police car could change the color of the traffic lights to be able to go faster through traffic. But of course, we can't let everyone have this power. So we need cryptography to enforce this kind of access control. So for our prototype, we need a transport layer, and we ended up choosing Zenoh because it matched really well with what we needed. So the idea behind broadcast encryption is to send one ciphertext to a big group. We envision hundreds of nodes, and we tested hundreds of nodes, but really it could be thousands of nodes. So using data-centric pub-sub communication, we need the multicast capability. So we need to send messages to many users. And our goal with broadcast encryption is to reduce the cryptography overhead. And we also need to reduce the network communication overhead. So Zenoh is great for that. And because we also fix the decentralized distribution of keys, we have so with our system, every user can generate their own key pair, publish their public keys. So it's as decentralized as we want. So for that, it's convenient to have a distributed peer-to-peer network configuration. We can have complex network topologies, so routers or peers that act as routers distribute messages, and several protocols can work with it. So Zenoh has been our choice with it. So now I'm going to give you a look at a typical protocol workflow. So we have our Zenoh network and we have devices, so we can see them as sensors or autonomous cars. Really, they're going to be the ones that have, so each have their own private and public key pair. And at the start, so using the query reply feature of Zenoh, they can declare their identity and public keys as a queryable. So every device will query the identities to know who is in the network. And now the messaging can start. So let's say that the devices 2, 3, and 4 subscribe to the topic taxi, and device 1 declares itself as a publisher on this topic. So now it's going to look like this. They're all members, publishers or subscribers of this topic. And device 1 is going to establish a target set. So by establish a target set, what I mean is using the hybrid encryption that we saw earlier, but with the broadcast encryption that we developed. So it's going to send a new symmetric key to device 2 and device 3 on the topic taxi. So this creates this target set, okay? So device 2 and device 3 are in the target set in blue. Of course, since device 4 is subscribed to the topic taxi, it's going to be able to see that there is information that is being sent, but device 4 does not have, as we discussed with the broadcast encryption, device 4 is not in the target set, so it can't decrypt this message. Now, device 1 is going to send a message. This time, it's going to use the symmetric key that it encapsulated and sent to 2 and 3 to encrypt this message. So device 2 and device 3 are going to be able to use this key to decrypt it and see the message. And as well, device 4 will see that something has been sent, but it looks like encrypted gibberish to it. It cannot decrypt it. And we are not limited with, so it's going to be one-way communication in the target set, but every device can participate. So for example, if device 2, so device 2 would need to declare itself as a publisher, but then device 2 could establish a new target set with only the device 1 in it, and would then delete the target set when it's done with it. So this was our typical workflow. Now about the way we integrated it with Zenoh. So we use topics for grouping, as I presented in the previous slide, and it's convenient. Everyone can subscribe to the messages, but our goal is end-to-end encryption. So we add this broadcast encryption layer on top of it, and now only the target set is going to be able to decrypt the messages. But the network topologies of Zenoh are very interesting because now messages can get relayed even by non-target set members. So even if you cannot decrypt the message, you can still relay it to act as a router, relay it to other devices. And yes, as I said, so we use PubSub for the messages and query reply for the identity management. So we to develop this this project and test it. At first, we used Docker containers, which are very convenient to prototype and and develop our project, where we had one container per device. But so as it is explained in the Zenoh docs, when you have too many Zenoh peers, Docker starts to break down. So we had our real benchmarks done on Kubernetes pods, where so we had one kube node and one pod per device, and with it we are able to easily simulate up to 500 nodes to validate our proof of concept. Now I'm just going to talk a bit about performances, but so here it's the time in milliseconds to encrypt, to encapsulate a key as a function of the size of the target set. And so as you can see, the canonical way of doing it would be to use RSA encryption, and this grows very high, very fast. So 2 to the 11 is 2048 recipients, and we are almost at a second to encrypt, whereas mKeeper, so in both cases it's linear, but we have an exponential x-axis, so this way it looks like it's an exponential. It's linear, but the coefficient for RSA is way bigger than for mKeeper. And now we compare performances between plain Zenoh, so just sending a message over Zenoh, and our system. And so we add some overhead, of course. So what's interesting is the green the green curve here is plain Zenoh. So it's more or less constant as we grow the number of receivers, and it's so very low overhead. It's in the name. With our system, we have a 3 millisecond overhead. This includes signature, encryption, and sending over Zenoh. Only using the symmetric key, because so in the blue curve is the establishment, which is encapsulating and sending with the broadcast encryption the encapsulated key. This does not happen at every message. It's just to establish the target set, and then so it's blue curve once at first, and then orange curve for the rest of the communications. So to conclude, the limits that we encounter are that, well, for now, so we use Zenoh as a separate layer from our project. The public key logic is separate from the Zenoh IDs. The topics and the target sets are managed separately, and we did not really use the ACL at all. But some idea that we have once, so it's possible to do it, would be to build Zenoh interceptors to have seamless integration. So as you can see, I represented the topic on top of the target set, but what we could have is really have a one-to-one match, and we wouldn't have to stack one layer on top of each other. They would be one and the same. So thank you for your attention. If you have any question about integration of security, you can of course contact us at Linear, and we'd be happy to discuss with you. Thank you. Hello.
Yeah, sorry, we were on mute. So Leonard, very interesting presentation. Thank you very much. I have a couple of questions for you, but let me check if there are any questions from the community. Can you in parallel? So interesting. Now, the problem that we have is the infrastructure, because nobody can. So we have data integrity, right? But we can still have omission if the infrastructure is not trusted, which is a problem. And so the question is, how do we bootstrap the infrastructure in a quantum fragile world?
So
it's no problem. You understand the problem, right?
So what you mean is that if in the infrastructure we
so imagine I'm a router.
Does not forward a message?
Imagine I'm a router, and actually,
yes.
So I'm a router because I mean, in Zenoh, when we build up the infrastructure, you can use security, but that would use TLS, right? So imagine that I've managed to break, I've observed sufficiently, I've managed to break, and I can inject a malicious Zenoh router in the network. It won't be able to, I mean, we have still integrity with your mechanism, right? We have let's say, confidentiality, but then I can do nasty things, which is very simple. I drop your messages. Okay, and so what becomes interesting is, can we use part of this new security technique to have a secure infrastructure? Because that's the other point, right? You need to trust infrastructure at least a bit, because I mean, as soon as I start behaving in a Byzantine manner, that that can create some, but it's super interesting. So you should come visit us. We have lunch together and we'll discuss some cool stuff. Okay.
Okay.
It's also based in Paris, right? I think that's worth mentioning, to the people that are online.
We are just nearby ENS anyway.
L'École Normale Supérieure is right across the road. Yeah, Central Supélec is that. Well, you know where we are based, right? Yeah. Okay, cool. Thank you again. Thank you for reaching out. Thank you for the presentation. Great work. So keep up with the great work. And again, I think we should have some session together. So let's organize that after the Christmas holidays. Okay.
Sure.
Okay. Thank you, Leonard. Ciao.
Goodbye.
Thank you. Bye.
And that brings us essentially to the end of the meeting. So guys, another year is almost over. We still have a couple of weeks. Well, there is an India Roscon waiting, right? Next week, indeed. And then we are about to wrap up a year. So it was pretty interesting and full year. So once again, thank you to you guys. Thank you to you guys. In fact, and lots of things cooking. So what I can say, we'll see you next year at the Zoom 26. Bye, everyone.
Goodbye.
Olivier?
Bye.